Yes, yeah, Sajan is joining. So once he will join, you can start, Dr. Sachin.
Sure, sure. Most of the delegates have joined.
No, they have not. There are now in total, it has increased. So there are almost 30 delegates, 29 to 30 delegates are there, 30. Out of 30, so 1, 2, and 3, 13, 10 only has joined out of 30. Sergeant will join.
Should we start, Mohit? Dr. Sajan has joined.
He is joining still, like there is connecting to audio, it is like that. It's taking time. Let him join because he is going to have the first lecture. Okay, I think so. Sajan. Yeah, Dr. Sajan, are you there? Good evening, Dr. Sajan.
Hello, good evening, Dr. Mohit. Good evening, everyone.
Good evening.
So Dr. Sachin is there. He is the our state and zonal coordinator for all the workshops.
Hello, Dr. Sachin.
He
Hello,
is
Dr.
a neonatologist. He has been running one of the big NICUs in South Gujarat, in that is in Surat, Anand Hospital. So he's been practicing for more than 15 years. है ना सचिन? 15 साल हो गए ना?
21 years हो गए अभी. Retirement
21 years. Sorry, 21 years.
That's a good one.
So I'm on the verge of retirement, basically. No more introduction now. So,
and then we have Dr. Vilas also with us, and she is the local coordinator at Nirmal Hospital. So she is a consultant neonatologist at Nirmal Hospital, Surat. And we have Dr. Kunal. He is one of the faculties, and he is presently the secretary of Gujarat NNF state. And he is a practicing neonatologist at Rajkot.
Hello, everyone.
Hello, Dr. Ravi Parekh has also joined. He is also one of the faculty. So over to you, Dr. Sachin.
Yeah, so good evening, everyone. I hope you all are very much excited about this online program on POCUS and FOCUS. I know most of you will be more interested into the hands-on workstation. But before that practical thing, let us start our today's session with the online version of the basic lectures. And you all are in the group, so you are aware of the program, what we are dealing today. So we are having 2 sessions of online lectures where you will get a brief about the basic views, the basic understanding of how the things work. And later on, in the workstation, you will be having a hands-on demonstration of all the things. So we have very very renowned personalities in the field of ultrasound and echo. And today, it's a matter of great pride that on behalf of the our West Zone Neocon team and SPAC team, I welcome you all for this wonderful workstation. Rather wasting much of the time, I will invite everyone and be more open about all your queries, all your questions to the faculties who are there. You can ask all your queries here online, and then on the workstation, you can have a detailed discussion. So wishing you all a very happy learning. And I would invite Dr. Vilas to welcome all the guests.
Dr. Vilas?
Yes, sir.
Yeah, switch on your camera and
Good evening, everyone. Respected seniors and faculty, I invite you all to this online workshop class. Today, we will learn about the basics of ultrasound and basics of echo. And first class will be on basics of ultrasound. It will be sir will take the class. Dr. Shiv Sajan Saini, sir. He is assistant professor at PGI Chandigarh. And he will take a class for next 30 minutes about basics of ultrasound.
so before we start with Dr. Sajan, and like I have listened to this session, no one, like I have the experience for the last 14 years, no one takes a better session on basics of ultrasonography in many of the ultra workshops I've seen. So we are really fortunate that this session he's been taking for us. So before we start with the session, I would like everyone to switch on your cameras if possible, if you are not in your washrooms, so that we can have a kind of group picture. And then we can switch over to Dr. Sajan, and so that he can start his session. So I would request everyone to please switch on the cameras so that we can have one screenshot. Yes, great. So I will be taking this screenshot. So if possible, please switch on your cameras so that we can have a group picture. And then we will also know that everybody is attending. It is not the bot, that your machines are on, your computer or phones are on, and you are getting this attendance. Okay. So I will take the picture now. Dr. Sajan, आपका कैमरा थोड़ा हिल गया है.
हाँ हाँ.
Yes. Yeah. So I'm going to take this picture. So everybody please smile. Okay. Great. Thank you. Oh, okay. I will take another one. Somebody has just switched on the camera. So I will take another one. Yeah. Great. ध्रुवी ने भी ऑन किया. ऑन कर लो यार सभी लोग. Yes, please on switch on the cameras. Yes. So I will take and this will
cancel कर देना उनका आज.
हाँ. ये अब लास्ट वन रहेगा. रवि चला गया. रवि पारिक. Okay. Fine. Yeah. Thank you. So over to you, Dr. Sajan. You can share your screen now.
Yeah, so thank you for the kind words, Dr. Mohit, and thank you everyone, Dr. Vilas and others, Dr. Sachin, Dr. Kunal for the kind introduction. It's not allowing me to share. Yeah, fine. So are you able to see the screen?
Yeah, we are able to see the screen.
And the voice is okay, right?
Yeah, voice is fine. Yeah.
All right. So good evening, everyone. I am going to discuss a quite boring subject. This is my disclaimer. This is the physics of echocardiography, basics of echocardiography. And I'm going to bore you for next 40 minutes. But this is important. before application, before applying any new tool, we need to read the information brochure, and this lecture is kind of an information brochure for the basic aspects. So I'll be discussing with the physics of ultrasound, a brief discussion about the physics of ultrasound and various modes which are used, what are the logic behind those modes, and how you can optimally use those modes to refine your images so that you can get best out of your images. So let's begin with the physics of ultrasound. So this is the kind of ultrasound machine. Yeah, so this is a I mean, a schematic diagram of ultrasound machine. This is attached to this is the probe, and this is the connecting wire between these two. So what happens? The electric signals, they excite the piezoelectric crystals. The piezoelectric crystals, they throw the ultrasound beams inside the tissues. They strike these tissues. These waves strike the target, comes back. They hit the piezoelectric crystals once again, and it is back converts these transducer that back converts these waves energy into the electrical energy. This goes to the ultrasound machines. Ultrasound machines then makes whatever is the whatever energy it has sent and whatever energy it has received. So it transforms into a image which we see on the user interface of the machine. So that's the purpose of these transducers and machine. So we all know that the speed of propagation of this machine, the sound is ultrasound waves inside the tissues are body tissue. It differs between the various tissues, but in the body tissues, it is approximately somewhere between 1500 to 1600 meter per second. Remember, it makes a two-way trip. It goes, hits, and comes back. So every wave, every ultrasound beam which is going inside the tissues, machine knows that when it receives the signals back, then it has made a two-way trip, goes, hit, and came back. So basically, it calculates time accordingly. So say, for example, it took say 4 milliseconds since the time the ultrasound beam has left the transducer and came back. So it knows that the object is 2 milliseconds away, as if we consider the one-way trip. So deeper is the target, it is going to, or intuitively, it is going to take longer time. The shorter is the target, it is going to take a shorter time. And we'll discuss it. What is the value of this? What is the importance of this information? And whenever a ultrasound beam that strikes an object, strikes a target, say for example, a heart valve or a heart tissue, there can be three consequences. A, it can transmit, it can pass through that particular organ or tissue. It can get reflected. All the things can come back, and if the anatomical target is impervious to that particular waves. And the third is scatter. So it can go here and there. It can go here and there, and the energy is lost in that. So what is acoustic impedance? Every tissue, once the energy, the sound waves, they are going, ultrasound waves, they are going inside, then it is striking an particular object. Now the objects inside the body, they are not a homogeneous object. There are some fluid. I mean, the blood is there. There is a pericardium which has got a different kind of resistive properties. The myocardium has different resistive properties, and endocardium has different resistive properties, and so on. So they pose a different kind of resistance to the propagation of these waves, because they have their impedance, and that how much resistance it poses is equivalent to acoustic impedance. So when the ultrasound waves, they are traversing through the tissues and passing from one tissue to another tissue, then the acoustic impedance of these tissue are likely to be different. For example, an endocardium and blood interface, the acoustic impedance of these tissue interface is going to be different. So whenever there is a mismatch in the acoustic impedance, then there is more reflection. If there is no, if the acoustic impedance is same, the ultrasound beams are travel in a kind of homogeneously, regular fashion. But whenever there is a mismatch between the acoustic impedance, then it is going to have reflection, more of reflection, and thus we are able to see these structures that there is this structure and this structure is different. Whenever there is a homogeneous surface where the reflection is different, but in inhomogeneous structures, inhomogeneous interface, for example, there is a certain waviness in that blood pool and endocardial interface, then the scatter is going to be way higher as compared to if it is a very, very homogeneous structure. So that creates a very striking image that the difference between these two, they appear different when we see them on the screen. That's how we are able to differentiate these two structure as two different structures. So when you have, you can see that there are certain white looking areas. So this is, say, this is a solid viscera, maybe most likely the liver, and you can see that there is diaphragm. So so we can see that there are certain tissues which are not as white as compared to the diaphragm, and we understand that this poses a very high acoustic impedance in comparison to the liver viscera. And thus these two here at these interface, because their acoustic impedance is different, then a lot of waves are going to be scattered, and we do see these two structures as two different structures. Next comes the concept of wavelength and amplitude. So what is wavelength? We know that every wave is composed of a peak and a trough. So this is a one full wavelength is the beginning of, it starts off as a peak, and then it trough, and then comes back. So this whole cycle is one wavelength. Okay. So if we know that if the wavelength is very long, then the wavelength is inversely proportional to frequency. So what is frequency? Number of wavelength in per unit time. And if you have, so they are inversely proportional. The longer is the wavelength, the shorter is the frequency. I mean, the shorter is the shorter is the wavelength, the higher is the frequency. Okay.
Madam.
So if we have, so can I request the participants to mute their
yeah, I am
microphone,
muted. I am muted. Yeah.
So if we want, so longer, the benefit of longer wavelength, the ultrasound waves of longer wavelength is that they can traverse to the deeper organs. So if you want to send our if we want to see the deeper structures, we want ultrasound with with the longer wavelengths. For example, to interrogate the heart, we need the ultrasound probes of say 5 to 10 megahertz. But if you want to see the deeper structure inside the abdomen, we don't need 5 to 10 megahertz. We are okay with say 2 to 5 megahertz kind of a probes. But if you want to see the superficial structures, the very superficial structures, then we need a very high frequency, so 10 to 15 megahertz frequency probes. Those frequencies which are very high have a very short wavelength. So the benefit of longer wavelength is that it can penetrate deeper. The benefit of shorter wavelength is that it can give very high frequency, but the flip side is that it does not go very deeper. And hence, if you use a very high frequency probe to interrogate the deeper structures, then we don't see the deeper structures because there are a lot of, the wavelength is very small. As they go inside, there is a lot of loss of signals, and we see all the black areas if you use a very high frequency probe to interrogate the deeper structures. So it has to be taken into consideration how deep you want to interrogate. For heart purposes, 5 to 10 megahertz is okay. And I said frequency is inversely proportional to the T. The other concept is amplitude, and this is related to energy, and we are not much bothered about amplitude, but we'll discuss a little bit when we see the little resolution. We'll discuss the resolution. So in this part, I have already told the distance is, so we know that the machine knows that once whatever time it has taken, the time is equal to the two-way trip. I mean, the time it has left, the beam has left the probe and it has come back. It has traveled it has made a two-way trip. So once we calculate the distance, it is calculated by applying this formula. C is the speed of the sound, ultrasound. When I say sound, I mean ultrasound. So C is the speed of the ultrasound, which is 1540 meters per second. T is the time. Machine knows what time it takes, and you applied C into T divided by 2. Then this is the distance from the probe to the anatomical organ of interest. Okay. So this concept we have already discussed previously, and the importance which I have already told, that the longer wavelength is required for better penetration, and a shorter wavelength, which means high frequency, is required for greater to see the superficial structure or greater resolution. And we'll discuss this concept in shortly in the coming slides. So to optimize image, we need these particular characteristics of ultrasound. We need frequency, we need depth, we need resolution, we need focus, we need sector width, attenuation, and so we will discuss them one by one. So frequency and wavelength we have already discussed. Let's take the component of depth. So this is an image of a this is a phased array probe, where the and this is displayed on the user interface as a sector. So this is the sector. So we can see that this particular thing is an orientation marker, which is equivalent to the orientation marker at the probe. This is close to the chest, I mean the wall, the chest wall, and this is the deeper structures. This is the deeper tissues. So we can see that we want to interrogate heart, and the heart is occupying roughly half of the screen. So when we don't use the adequate depth, so in this particular image, this particular depth, the person is the interrogator, the echocardiographer was unable to use. So it was useless. He opened up heart only, he chose an inadequate depth, and that's why whatever measurements he's going to do are likely to be more erroneous as compared to the other one, where we know that I have put the heart, I have expanded the heart almost to the down of the screen. Well, I have had a very good visualization of the structures, but then I may lose the sight of measurement, because the measurement may, when the tissues are moving, the tissue may go out of the window and I may lose the adequate measurement. So what is the adequate depth? So adequate depth is when your anatomical area of interest occupies 2/3 of the your sector. So 2/3 depth, that is an adequate depth. The same is depicted. This is a short axis parasternal view, and we can see that this is barely occupying 1/3 of entire slide. If we optimize, then this is the kind of adequate depth, which is occupying almost 2/3 of the window. The second comes resolution. The resolution is, there are several concepts behind this resolution. So I'll take them one by one. So one is detail resolution, one is contrast resolution, and one is temporal resolution. The detailed resolution is when we are, the ability of machine is to depict the two structures as two different structures. That is the detail. We are interested in the details of that particular organ. Contrast is when we want to show one structure is different from the other. So that is a contrast. And third is temporal resolution, which deals with the motion of the ability of a machine to pick up the whether the structures have moved over a period of time. So that is a contrast resolution. So we'll discuss them one by one. So the detailed resolution are two types. One is axial resolution and one is lateral resolution. So axial resolution is discriminative ability of the machine to identify the two objects which are lying along the ultrasound beam. And what do I mean? So these two structures, so this is the schematic diagram of a probe, and these two structures, they are lying in line with the ultrasound beam. So ultrasound beam is going like this, and these structures are in line. So ability of machine to identify these two structures as a two different structures is axial resolution. Okay. So how does it machine differentiate these two structures? So machine is going to throw a beam, and this is one wavelength here, from here to here, and this is the second wavelength, this is the third wavelength, and so on. Okay. So it has the 1, 2, 3, 4, 5, 6. So 5 or 6 pulses wavelengths. This whole structure whole depth has covered. Now what happens? Look at these two structures. So beam is starting here and is going, and the one pulse is that this is the fourth pulse, and the fourth wavelength. The fourth wavelength starts from here and goes. So now these two structures are lying in the fourth. Both the structures are lying in the fourth wavelength. So now this machine, when these structures will hit this machine, the wave will hit this. The ultrasound wavelength will hit these structures and come back, and then it will hit this structure and come back. So although they are two different structures, but the same wavelength is going to hit. So fourth wavelength is going to hit and come back, fourth wavelength is going to hit and come back, and machine will be unable to differentiate these two structures as two different structures. It will read them as a single structure because the fourth wavelength has hit both these structures and came back and give it information. The time is almost the same, and a machine will be taking them as single structures. Oh, look at now. So this is the we have taken a high frequency probe where there is a shorter wavelength, and now these two structures are falling in two different wavelengths, and now this structure is hit by the, say, sixth or seventh wave, and this structure is hit by the next wave. So now the machine is able to differentiate these two structures as two different structures, two objects as two different objects. So what do we learn? That our axial resolution depends upon the frequency of the probe, and higher the frequency, the higher is the axial resolution. Okay. So this trade-off, there is a trade-off between resolution and penetration. So I have discussed it. If we use a very high frequency probe, then we will be unable to interrogate the deeper structures that we have already discussed. What about lateral resolution? The lateral resolution is ability of the machine to identify these two structures which are perpendicular to the line of ultrasound beam. On which factor it will depend? Suppose this is the wave, this is the single wave which is going. Now, if they are interrogated by the different waves, it will consider these two structures as two different structures. But what happens in the real time? The real time is, in the neonates, we use the phased array probe, and which has got a very small footprint. And the waves, when they go inside, they diverge. And because of this divergence, you have seen previously in the previous slide that it forms a sector kind of a visual display on the screen, on the user interface. So once they go apart, then lateral resolution is likely to be compromised. So what is the way out? So the way out is the focus. You have to use the focus of the ultrasound machine to optimize the lateral resolution. So once this probe throws the signal, then it goes inside, and instead of diverging directly, the machine asks these the beams to converge to the focal point and then diverge. Okay, so you can use the focus near and far depending upon your anatomical area of interest. So if your area of interest is, say, like this, you can adjust the focus of the we'll shortly see how to adjust the focus, but you can adjust the focus up and down depending upon your area of interest. And second is, higher is the frequency, it is associated with lateral resolution, and narrow is the sector, it is associated with lateral resolution. So basically, these are the three ways to improve the lateral resolution. So this is how you we can adjust the focus. So once we have this visual display of this sector phased array probe. This is a sector, and there is the slide the cursor orientation marker, and this is the depth. These small dots is the depth. It will be written, every machine will write here this 5 millimeter, 5 centimeter or 4 centimeter, or etc. etc. It is equivalent to the depth, and there is the focus. So middle point is the focus, and it has got some a whisker, and it's kind of a box and whisker, central dot and a whisker. So you can make this focus, you can shift this focus up and down depending upon. So I want to see the, say, this is the long axis parasternal view. This is the mitral valve. This is the left ventricle. This is the left atrium, and this is the aorta. And this is the aortic valve, and this is the mitral valve. So if I want to study the mitral valve, I better keep this on at the level of mitral valve, and you can see that this valve is better displayed as compared to the other structures in on this image. Okay. So that is how you use the lateral resolution. You improve your lateral resolution. The next is the temporal resolution. So temporal resolution, we have discussed that it is ability of machine to identify that a particular object has moved from one place to another. So it is synonymous. So it is synonymous with the ability of the machine, or lateral resolution is synonymous with the frame rate. So what is frame rate? The frame rate is so the machine has takes some time to scan one frame. So there is one beam, it goes and it scans entire frame. So the time it takes to scan an entire frame is it one frame, the rate. So the frame rate is 1 divided by the time the machine takes to scan the entire frame. So intuitively, if the time taken to scan one frame is higher, the frame rate is lower, and if the time is lower, then the frame rate is higher. Time taken to scan one frame is lower, then the frame rate is higher. So the time to scan one frame is directly proportional to the pulse repetition frequency. So the which is synonymous with the frame rate. So, and higher is the frame rate, higher is the pulse repetition frequency. I mean, I'm loosely using the pulse repetition frequency, but it is actually the frame rate. So the higher is the frame rate, higher is the temporal resolution of a particular of the particular ultrasound. So we'll use the pulse repetition frequency once we discuss the M mode, but the concept is the same. Okay. So how do we improve the frame rate now? The next logical question is, how do we improve the frame rate? So intuitively, lower is the depth, the higher are the number of pulses per second. So higher is the frame rate or pulse repetition frequency. Now the second is, wider is the sector, the more time it takes to scan entire frame. Narrow is the frame, the lesser it takes to scan the entire frame. So the lesser is the depth, the more is the frame rate. The narrower is the sector, the more is the frame rate. So this is how we improve our temporal resolution, by decreasing the depth, by narrowing the sector, and by using the higher frequency. They all are means to improve our temporal resolution. So next comes the contrast resolution. And contrast resolution, what is the contrast resolution? That once we throw some signal inside the tissue, as they go deeper and deeper, you can see that these structures are very well displayed, but as this goes deeper, these structures are not well displayed. So what is happening? The beams are going down, and once they are going down, they are going to lose the energy, because the waves are getting, they are hitting an organ or tissue. They are getting distracted, they are getting lost, they are absorbed, etc., etc. So less number, as they penetrate deeper and deeper, the less number of the more is the loss of energy and less number of waves are reaching deeper down the tissues. So now, as they are getting lost, the objects are appearing more and more black as they go down. So how to visualize this, how to improve this resolution, this is something we are going to learn in the next few slides. We use the gain function to improve the contrast. What does gain do? So as we go down, the objects are hitting, the ultrasound beams are hitting the anatomical objects, they are coming back, hitting sub objects, they are coming back, and then they are the number of waves or kind of energy which is getting refracted from this place is likely to be higher than energy which is getting refracted from this place. Therefore, these tissues, they are appearing more black, and these tissues, they are appearing little white, and they are more white. So this is natural phenomena, and the reason we have discussed. So what by gain functions, we are going to increase the kind of energy which is getting reflected after hitting the anatomical organs. And once we improve the, once we amplify this energy, we see something like this. So this is the normal image, and we have increased the gain. Then we tend to see this structure. Now the problem is that although we are able to see the deeper structures in a better way, but what is happening here? Here it should be black like this because there is no tissue here. There is blood. So, but you can see that there dots. So hazy, snowy appearance has started appearing. So which means that the tissues, even with the very small kind of a with a small reflection of the Doppler now signals, they tend to the machine tend to amplify those signals and project them as if there are some real objects. So that is kind of a noise which the machine has created. So you can get false kind of reassurance that, or not false kind of images, that you can see that the structures which are there, but they may not be there, and which is because of the phenomena which we have discussed. So what is the way out? The way out is, and this is another depiction of this 2D gain. When we increase the gain, it improves the signal in equal proportion from the nearby tissues, and it increases the, if it increases the 50% energy from this area, it increases similarly 50% from these two areas. Whereas these two areas are appearing much better, this area, nearby areas, they are appearing much more snowy. So what is the way out? The way out is time gain compensation. So now the time gain compensation says that what we do with time gain compensation. So consider this equivalent to, so this is these are the various knobs given by the machine. This knobs is for increasing the gain of a deeper structure, and this particular knob is related to the gain functions of a nearby structure. So what I have done is I have minimized the gain, kept this knob on extreme left end so that it is not increasing or increasing to a very say 10%, whereas this is increasing to much higher, maybe 60-70% gain of a deeper structures. So now if I throw the signals, I will see these image as a nearly homogeneous kind of an image, and it's because of the differential gain as for the deeper structure as compared to the superficial structures. So this is known as a time gain compensation. This is another view to suggest the time gain compensation, and you can see that these two structures were much better. This image is much better as compared to the previous image where we had increased the gain. We use the whole gain function to increase the gain of the machine. So we all know that there are various types of transducers. This we have discussed up till now. This has got a very small footprint. This is a sector probe or phased array probe, very small footprint, and the visual depiction is of a triangle on the user interface. Here we have our second is a linear probe where the footprint is much larger, and we see the rectangular image of sector on the user interface. And this is usually a very used for very high frequency measurement, say something like 10 to 15 megahertz. The another is a combination of these two. This is a curvilinear probe where the footprint is much larger, but and similarly, accordingly, the user interface shows you a curved kind of a combination of sector and a curved kind of a visual depiction of the ultrasound on the user interface. Tissues on the user interface. So now coming to the modes, there are different modes: 2D mode, M mode, and Doppler mode. You must have heard or must have practiced, but let us study them one by one. What is 2D? 2D is two-dimensional, which means that the ultrasound beam is two-dimensional when it traverses the tissue. So this is the schematic diagram of heart. This is an ultrasound beam which is thrown by the transducer, and this is in form of a sheet which has got an x-axis and y-axis. So as it goes inside, it cuts the heart, or it interrogates the heart in such a way that as it goes down, it cuts the heart into two identical halves, and this is depicted on the screen like this. So we know that this is the orientation marker, which means that this tight structures, if I keep my transducer in such a way that our cursor orientation is towards the left side, so this tight structures are left-sided structures, and this tight structures are right-sided structures. So this is left ventricle, this is left atrium, this is right ventricle, and this is right atrium, this is interventricular septum, this is interatrial septum, this is tricuspid valve, this is mitral valve. And this was possible. This is the 2D image. And this was possible because my ultrasound beam cut the heart in such a way that, it has got a two-dimensional ultrasound beam. Because of this two dimensions, I could have a two-dimensional visual display of the heart. So you can see the heart beating if you use the sine loop function. Then there is M mode. What is M mode? M is the motion mode. It stands for the motion mode. So if there is a single ultrasound beam, is a single line. This does not have an XY plane. This is single line. It has a single axis, one axis. Okay, so it does not have a depth. So it goes and cuts the anatomical, the heart in various chambers and various tissues, whichever are coming across this line. So we know that this is a long axis parasternal view, and this is right ventricle border. This is interventricular septum, and this is left ventricular posterior wall, and these are the two mitral leaflets. So the beam is cutting all these structures, and so these structures will be displayed on the screen in such a way that this is the time, this x-axis is the time, and y-axis is the visual display of these structures. So the line is cutting the right ventricle, and the right ventricle is displayed here. This is the right ventricular cavity. This is the right ventricular cavity. This is the interventricular septum. Now this is the interventricular septum, and this is the posterior wall, and this is the posterior wall, and these are the two mitral leaflets which are displayed here. So anterior mitral leaflet and posterior mitral leaflet. So now you can see that now the heart undergoes a relaxation and contraction. Whenever the left ventricle is contracting, they come closer to each other. So this is end systole and this is end diastole. This is the end diastole where they are farthest apart. So if we are able to capture the motion of these according to as per the timeline, which is on the x-axis, we are able to capture the motion of the moving structures, and this was possible because of this M mode, which was cutting. So the leaflets will be moving like this. They will be moving like this. So as they will be moving, the beam is cutting those structures and their motion is reflected here. So we know that when they are going apart, it is diastole, and once they are coming together, it is systole. Okay. So M-mode application, we have understood that we can calculate, these end diastolic dimensions of left ventricle and end systolic dimensions of left ventricle, diameters, and we can use these diameters to get our favorite indices like fractional shortening and ejection fraction, and we'll discuss them later on. So this is the practical application of the M-mode. What is the advantage of M-mode? M-mode has got a very high temporal resolution because it has got a very high frequency or pulse repetition frequency. So that's why if we tend to calculate the distance between these two moving structures, better to use M-mode rather than the 2D mode. You can use 2D mode also to calculate the distance between the two moving structures, but because of the pulse repetition frequency, the measurements are way better in M-mode as compared to the 2D mode. So let's discuss now the Doppler principle. So we all have heard the train moving, approaching the platform, and once we are standing there, the train blows a horn, and once it is whistling, and once the train is coming towards us, there is much amplification of the signal, and it is the signals exponentially, the volume of the signal exponentially falls, and this is the practical application of the Doppler effect. So machine is coming with the speed, the energy in the sound wave, which is throwing the energy of the machine is added to the sound waves, and there is exponential rise in the signals because of the Doppler effect. And then once it leaves, there is a equally exponential fall in the auditory. Once we listen the signal, it exponentially falls because of the Doppler effect. So how do we scientifically say that scientifically understand what is Doppler shift and its principle and its application? So this is schematic diagram. This is an RBC and this is the ultrasound probe. So now the probe is going to throw a beam. It is going to strike. So it is going to strike, and then there is a certain energy and associated with it and certain frequency associated with this. So the transmitted beam has got a frequency, we depict it as Ft. So that is the frequency of a transmitted beam. Now it is going to hit and come back, and this energy is frequency, and this frequency is reflected frequency. So Fr. So now if the object is stationary, the frequency which is transmitted is equivalent to frequency which is received. There may be some loss of signal, but the frequency is same. But what happens once this structure is moving? So because now the structure is moving with a certain energy, now the frequency of this transmitted wave is going to strike, and the reflected wave will gain some frequency which is higher than the frequency which is transmitted. So obviously then once the reflected frequency is higher, then the difference is known as the Doppler of FD, or the frequency of the Doppler shift. So now this Doppler shift we are going to capture, and after capturing this particular just a second, just give me a second. Good evening. I'm in a web meeting, so I'm taking lecture. So just call me after half an hour, okay? And just convey it to the other, labor room team. Huh? Okay. Bye. So sorry for this call. So then, machine knows that if the Doppler shift is positive, which means the frequency of the received signal was higher, then the object must have been moving towards the ultrasound probe, right? And if the frequency of the received reflected wave is lower, then the object must be moving away from this probe. So because now there is a difference in the frequency of these probe, the machine knows whether the object is moving towards or moving away from the probe. Now this is the application. This is what is known as Doppler shift. Now how do we use that? We calculate it by using these formula. This 2 is because it is moving. This is taking a two-way trip. So frequency of the transmitted signal multiplied by v, which is the velocity of the object inside, and c is the frequency of the ultrasound beam, which is 1540 meter per second, or speed of the ultrasound beam. So because we know this, we can calculate the Doppler shift, and because the machine knows the Doppler shift, then machine can back calculate the velocity by putting this formula. And this is how machine calculate the Doppler, the velocity of this particular structure, be it a tissue, be it a valve, or be it a blood. So because we can calculate the velocity, and it has got a profound implications, because we can calculate the velocity and we can apply it to various formulas like Bernoulli's theorem, etc., to understand the pressure difference between these two particular construction. We'll discuss them shortly. So, but the real life is not so simple. You know, the object may directly move toward the ultrasound probe, which means that it is moving directly in line with the probe. But in real life, the object does not move in that direction. The object may move at an angle. So there is always an angle to the motion of the ultrasound beam and motion of the object inside the body. So this angle, which is theta angle, it kind of confounds our measurements. And why it is why it does confound our measurements? It's because then the formula now, it is not V upon C, it is now V cos theta upon C. And we know that cos theta, if we make it 0, which means that object is moving entirely in line with the ultrasound beam, that the cos 0 is 1. So which means that the V is the velocity, which was original velocity of the object, is perfectly captured by the machine. Once machine puts into back calculate the velocity from Doppler shift, the machine will calculate the exact same velocity with which the object was moving inside. But what will happen? But if the velocity is theta is 90 degree, which means cos 90 is 0, then V cos theta becomes 0, and anything upon C becomes 0. So which means that machine will perceive that object is not moving at all. Which means that if if the blood is moving in this direction and ultrasound is moving in this direction, then the machine will perceive that there is no flow of the blood inside the body. So this is important because there has to be a permissible angle up to which we can capture the real velocity, and above which the velocity measurements will be confounded, and that angle is 20 degree. So we allow only a 20 degree between the line of beam axis and line of the object of, the motion of the object inside the body. So if your motion of the blood is, or motion of the tissues inside the body is at an angle of the beam line by more than 20 degree, then it is all the measurements or all the velocity calculated by putting in these formulas, they are likely to be underreported and they are false. Okay, so try to align this object of the motion, the motion of the object inside the body with the beam line as much as possible, so that our measurements are correct. Okay, so I'll skip this. This is the same thing which I have discussed previously. Now there are three types of Dopplers. One is continuous wave, one is pulse wave, and another is color Doppler. We'll discuss them one by one. So what is continuous wave Doppler? So continuous wave Doppler is the machine is throwing the signal inside. It is getting reflected at various points. It is coming back. And once it is coming back, there is a fair degree of overlap. So it is diverging. Basically, the signals go inside, it's diverging. And once it come back, they are coming back in this fashion. So there is a great amount of overlap between these two. And the center of this of this overlapping region, that is the best area where we can get the Doppler shifts, maximum Doppler shifts. So how do we get that? There is whenever we align our the continuous wave, there is a beach circle, or there is a diamond shaped structure that comes in between the line. So that is an area where that is diamond or circle you should align wherever you want to see the maximum Doppler shift. So if there is a origin of tricuspid regurgitation jet, you put the center of that diamond or circle at the Doppler shift, and it gives you the best kind of measurements. So this is the visual depiction. This is a transmitted signal. This is the received signal. And then once you overlap these two, then the machine has got software to overlap them. Then it smoothens it out after filtering. This is the Doppler shift, and this is how the machine interprets that there is difference in the velocity of the signal from the transmitted, and the whatever is the velocity of the signal is calculated based on this Doppler shift. So how do we use that? This is just an example. So say, for example, there is a tricuspid regurgitation. This is a valve, this is mitral valve, this is tricuspid valve, this is tricuspid valve, and this is one chamber and this is another chamber. So say, for example, this is the ventricle and this is the atria. So the blood is moving with certain velocity, and once it leaves the ventricle, in the atria, the velocity tremendously increases, because we know that Bernoulli's theorem say that once it passes through a constriction, the velocity increases. So once velocity increases, because V1 is very less as compared to V2. So this is how P1 minus P2. This is a complicated formula. So we'll simplify it, because V1 is very less. We'll drop it, and the equation becomes P1 minus P2 is equal to 4V square. So now we know the velocity, because we know we have put our continuous wave here inside the atria, and we have checked what is the velocity. Say it is 4 meters per second. So we'll put it into formula. So we know that it is say 4 meters per second. So 4.2 meters per second. We'll put it into the formula 4V square. It's 4.3. So it simplify, and it calculates 74 millimeter of mercury. So that is what machine depicts here, 74.9. So this is how it calculates. It gives you a tricuspid, the gradient between one chamber and another chamber. So if you want to calculate the systolic pressure, you have to add the right atrial pressure to this gradient. And if you add the right atrial pressure, then it becomes a systolic pressure, because this was the pressure of 75 was gradient with the inherent pressure of atria against the inherent pressure of which is 5 to 10. So you add 5 to 10, and it gives you right ventricular systolic pressure. So this is how you calculate whether there is the pulmonary arterial hypertension is there or not. So now second is the pulse wave. So up till now we have learned that this calculates this continuous wave Doppler. It calculates Doppler shifts all along the line. So where we use this? We use tricuspid regurgitation in any form of signal which has got a very high velocity. Because this continuous wave Doppler calculates the Doppler shifts, which is maximum anywhere along this line. It has got no upper limit. And because it has got no upper limit, sorry for the disturbance. So because it has got no upper limit, then there is nothing known as aliasing or loss of signals, or which we will discuss shortly. And there is a related concept of Nyquist limit, which we'll discuss shortly once we discuss the pulse wave Doppler. So what is pulse wave Doppler now? What is pulse wave Doppler? Now the pulse wave Doppler is used when we want to check the velocity at a certain point. And what is the practical application of this? So suppose I want to calculate the velocity at this particular point. Say for example, this is a four chamber schematic diagram. But suppose I open up the heart and so I want to know the velocity against the aortic valve. Sorry, not against, at the aortic valve. I want to calculate how much blood is flowing across the aortic valve. For this, I want to calculate the velocity at the aortic valve along with some certain other measurements. So the critical piece of information is what is the velocity of the blood at the aortic valve. So if I have to calculate, I have to put my range gate at the level of aortic valve. Only then I will be able to calculate. So what does pulse wave Doppler do is it calculates the change in the frequency or the Doppler shifts in between these two range gates. Okay, so there is a Doppler line, there is a range gate between which it will calculate the Doppler shift, and if we have to align this range gate at the anatomical area of interest. Obviously, you will adjust the gate width accordingly to calculate, because if you keep it too big, then you will lose the sight of you want to calculate exactly at this point. If you do it too big, it will calculate to Doppler shifts from some other areas. If it took it too narrow, then it will be a problematic again. It will be there will be loss of signal. So a 2 millimeter range gate is an ideal range gate. So now the blood, but the problem is that blood may flow in this direction. So you have to align your pulse, the ultrasound beam with this line so that your measurements, this angle is minimized and this angle is less than 20 degrees. But in certain cases, if you are forced and there is, you have no other choice, you can use angle orientation, angle correction, but angle correction almost always, exaggerates the results, and thus it is advisable that at least in research setting, you should not use these information. So now let us come back to the our transmitted signal and received signal. So because the ultrasound is now, the beam is calculating, the machine is calculating signals, processing signals between these two range gate only. So suppose this is the signal which was passing through the range gate, and this is remaining signal. This is again range gate remaining signal, and this is how it is going. And again, this is hitting the anatomical areas and coming back. So this kind of a machine will overlap them. And you know that here there was no actual signal, but machine knows that possibly this was the, it has got some dots in mind that probably this was the signal which was sent. Which is fairly, constant. However, the transmitted signal may be different. It depends upon how much was the Doppler shift happened during that very narrow period. So once it overlaps, it calculates that okay, this was the Doppler shift, and once it the overlap these two and calculates this is actual Doppler shift which is received. And this is the perceived Doppler shift, which is dotted line is joining the actual ones, the bold ones. So this is what machine calculates, and this is almost invariably faulty, especially if the signals is having a very high speed. Now we comes to the most critical component, which is the Nyquist limit. So the continuous wave Doppler, we have discussed previously that there is no upper limit of Doppler to calculate, but no upper limit of Doppler shifts. But pulse wave Doppler, it has got an upper limit, and it is because of the reason which I was going to discuss now. To measure the frequency of cyclic signal, the sampling frequency, the frequency of the ultrasound beam should be more than twice of the frequency of the motion of the object. So object motion, suppose blood is flowing, it has got a certain frequency. So our sampling frequency should be more than twice as the frequency of the signal inside the body. So if we make it, simplify this, the Doppler shift, which is maximum Doppler shift, it should be plus minus half of the pulse repetition frequency. Pulse repetition frequency is the number of pulses which are sent on a unit time. So if my Doppler shift is of more than half of the pulse repetition frequency, then I am going to have a loss of signals, and which is known as aliasing. And let's see how. So this is the signal. This is the frequency of the signal. Okay. And this is the number of pulses which I'm throwing inside. So 1, 2, 3, and so on. So there are various pulses which are thrown inside, and this is the frequency of the signal. Okay, so this is one wave, second wave, and so on. So remember these pulses which I'm going to send, they are going to cut this wave, this frequency at certain points. And once I join these dots, the Doppler shift exactly matches this particular the frequency of the signal of the object. But if the frequency of the signal is very high, and we know our signal of pulse repetition frequency is same. So now the signal frequency is increased. So now it is going to cut this at this particular point. This pulse is going to cut by signal at this particular point, and so on. And once we join the dots, now the Doppler shifts the Doppler shift is very different from the frequency of the signal. So now, because it is very different, there is a loss of signal. There is a loss of data. Now, this loss of data is represented on a screen as aliasing. So what is aliasing? So now this is the Doppler shift which is going to be depicted. Now there is so this is the half pulse repetition frequency, which is our Nyquist limit. So anything which is above this Nyquist limit, it is not going to be represented, and it is going to come as an add-on signal above. So I'll show you how. So this is how you see on the screen. So this is actually this is the actual image. So this image. This is the diastole, this is the systole. So there is a velocity time integral. So because it has crossed the signal frequency, has crossed the pulse repetition frequency, more than half of pulse repetition frequency. Now it has crossed the Nyquist limit. So thus the remaining half is presented at the bottom of the screen, and this is known as aliasing. If you see your signal like this, then you automatically conclude that your lot of your information is stolen. I mean the data, I mean the measurements which you are getting out of this particular image, this is inadequate, and the velocity of signal which is measured by the machine is suboptimal. So how to handle that? Don't use this. This is usually people do. This is a cosmetic improvement. This is not a real improvement, because the Doppler shift is actually is the same. If you do the baseline, if you decrease your baseline shift, you can see the full velocity time integral, but that will not be your measurements will still be suboptimal. So what you do, you increase the Doppler frequency. You choose a higher frequency probe. Decrease the frequency. So, but it is not possible to decrease the frequency because you want greater penetration also. So that is not a very good option either. So then we increase the scale, which indirectly increases the pulse repetition frequency. What it does is it improves your visibility, and you get your pulse. Once your increases the pulse repetition frequency, then your images are depicted in a much better way. The aliasing is gone, and your measurements are correct. So now the last is color Doppler. By convention, we tell the machine that, okay, we display my image in two colors: red color for positive Doppler shifts, blue color for negative Doppler shifts. So anything which is appearing in red, it means that machine knows that this blood was moving towards the probe. And anything which is appearing in blue, machine knows that it is moving away from the probe. And there is a scale to it. So you can increase or decrease your scale depending upon the baseline velocity or baseline frequency of the signal. So for the signals which are very low velocity, for example, venous flows, you make it, say, decrease it by, say, 30 to make it between 30 to 40. Certain high velocities you increase to, say, arterial flow, you increase to like 60 to 70. And sometimes when the flow velocity is very high, regurgitant speeds, then more higher scales are needed. It is just a description that, okay, now we know that this was the high parasternal view. This is pulmonary artery and this was the PDA. So I know that PDA is moving. This is where the descending aorta lies, and this because it is red, I know that the blood is moving from the descending aorta towards the pulmonary artery, and this is left to right shift. This is how we use the color Doppler. So to summarize, we use frequency to increase the resolution, and we decrease the frequency to improve the penetration. For ideal depth, the anatomical structure should occupy the 2/3 of the screen. The higher the frequency, the higher is the axial resolution. The higher the frequency, the better is the focus. You can optimize the lateral resolution. To improve the temporal resolution, you increase the frequency and you decrease the sector width to improve the lateral temporal resolution. For attenuation, you use gain, which symmetrically increases the whiteness of the data, and time gain compensation, which differentially improves the depth-wise, improves the signal's whiteness. 2D is used to explore the anatomy, and it interrogates the heart in 2 dimensions. M mode, it interrogates in single dimension, single line. It has got a very good temporal resolution, and so use preferentially to measure the distance between the 2 moving structures over and above 2D image. Continuous wave Doppler is a good way, is used for all recurrent lesions or any lesions where to pick up any velocity where the blood flow velocity is very high, more than 2 meters per second. Pulse wave Doppler is used to measure the velocity at a particular given point, but remember that there is phenomena of aliasing which can happen, and if the pulse repetition, if the frequency of the signal is more than half of the pulse repetition frequency, so to improve that, you increase the pulse repetition frequency of the signal. So thank you very much. I will be happy to take up a few questions. Over to you.
Okay. Just a minute. Last technical hitches. Okay. Good evening, everyone. So today we are going to do the practical hands-on sessions on this machine. What this machine tells us, how to on it, how to switch off it, what to take care of it, how things can go wrong with this, and how we need to improve with this thing. So it will be like a practical session of what Dr. Sajan has told you. Fine. So this is the machine which we have in our unit. This is a machine which we have in our unit. So first of all, I am actually switching off the machine. I'm switching off this machine, and this machine is actually shown as on. So this machine is attached to where the UPS is written. You can see that we have written a UPS over here. So please attach it wherever the UPS board is there, so that you don't lose the data, and while it should not get switched off. Actually, fine, when you are doing it. Even there is a battery backup, but always try that you are switched on with the UPS board. So now I'm just switching on. This is a button where we switch on. Just press it once lightly, and this will get on. So it will take some time to get on, but don't rush to do the echo immediately. Let it get on. The data has to be stored. You will get all the parameters over there. Then we go ahead with the doing our work. So now there is a name is written over here. You can see there is some number written over here. And then this is today's date, 21st September 2024. Time is 8:22. CRD is the cardiac probe, which we will be using with a P10 frequency. MI is the mechanical index. TIS is the thermal index. We are not going to change it. These are just the parameters. This is the battery. It means it is getting charged. And this blue color, which is coming over here, it means the data is getting restored in our machine. Fine. Okay. So, because first of all, we have to learn where to use the machine. So this machine has different parts. This is screen part. This is the keyboard part, and other keys are over here. Then another part is we have the probes. We have the probes over here. Fine. So we'll discuss about one by one each of them. So I think the screen part should come first. Please see that. See the screen part should come first. So we have discussed that these are the screen. parameters. What is written over here will come after the keys are there. Okay. So you can see in the keys, I think I will remove this part. Okay, this is just to prevent from the dust actually. Okay, so you can see this part. Fine. So these are the QWERTY keyboards. That is Q, W, E, R, T, Y, U, what exactly what we have in our machine. Then there is something which is written as setup, report, review, and the patient. To set up what when we press any of the keys, something will be displayed over here. So I press the word setup. So when you press setup, so there is something what administration has to do. The annotations, the audio, battery, keyboards, everything. So this is actually setup done by the administrator. Yeah. This setup is done by the administrator. We don't change these parameters anytime. So audio, battery, like whatever it is done, we don't press the reset button because it will ask me many other things because calculations are already there in the machine. Fine. So nothing to do with the setup. So I'm going back, done. So then report, then review, then the patient. So we'll go with the patient first. So I'll press the word patient. So it's asking me that this was done by the earlier for this Akshay, new, these are the names of the patient. So what we do is we press the button new and end the last exam. So I'm pressing new. New means the last name, first name, and the middle name. So I'll write the first name and the last name first. So first name is like you want to write baby of Shweta. Last name maybe Garg. So I'm just creating it hypothetical. Baby of Shweta Garg. You want to create the ID. ID maybe any ID 23679 23456. Date of birth. The baby, when was the baby born? So baby was born yesterday. So month is 09 and the date is 19 or maybe day before yesterday. And the gender is the male or the female. I read the female. Then who is the user? Like I am the user. The indications of doing this for the cardiac part. And then exam. Exam type means I want to do the cardiac examination or the neonatal examination, which means the cranium part, or I want to do the abdomen. So I want to do the cardiac, so I'm pressing the cardiac part. So heart rate, blood pressure, whatever parameters you have, then the referring doctor, and then we say the press done. So these parameters will be displayed in the report part also, when you review also, and when you see the screen also. So when this R glass tells you it is taking some time to get that code. So now we get the Garg, baby of Shweta. This is general examination. This was the ID. This is date and the time. And this again with parameters which are displayed over there. Fine. So then if I do the echo of this baby, like I do the echo of this baby, and I store the images. What will you get? You will review this button. Once you're done with it, you will press the review button and you will get a list of the patients which were done. So last patient which we did was the Akshay, the Pratibha, the Payal. So if I want to review for the Pratibha, I just press this and press review. So it tells me 9 out of 9 images. This is 9 out of 9 image. I can have 8 image, 7th image, or if I press this play, so then it will load and it will show me what has been stored for this baby, and I can review it later on. So this is what has been stored for this baby. Fine. And I can take this data into my pen drive or I can archive it. Fine. So when I press it, I get export to USB. These are the 2 USBs. You can show this. So these are the 2 USBs, 1 and the 2. Wherever you want to store, you can store it, or you can archive it directly into your laptop by using the cable wire. Fine. If you want to delete, you can delete it. And if you want to go back, you're done and you go back. Fine. Once you press the report button, so this is the report, like for which baby I have done is Garg, Shweta. So everything is reported here. So once I do this exam. So till now I have not done the exam. So once I press the exam, so these details will come on one page and the other images will come on the next. Okay. So now coming to these buttons, the lower ones. So what is happening over here is, so this is the central joystick. So if you want to move the image or anything, so if I want to move this arrow, whatever is shown here. So I can move like this with this joystick. I think this simple thing. Fine. It's like a touchpad for a laptop. Same thing. So then this is central one. I'll come to the modes first. So this is the M mode, the Doppler mode, the color mode, and the 2D mode. So 2D mode is the brightness mode, which Dr. Sajan has told you, the brightness mode. Then this is a color Doppler mode. This is simple Doppler, the continuous, and the other Doppler mode, the pulse wave Doppler. And this is the M mode, the motion mode, or the where we do all the measurements are done in this mode. Fine. Then update, I'll tell you once I do start doing the Doppler, then will come. So if I press the 2D, so I press the 2D, this comes as sector, everything, the page 1 to 2, and then this is shown over here. Fine. Clear? If I press the color, then what is shown, a scale has come over here. Scale 78 plus to 78 minus, which means 78 meter per second to less than 78 meter per second, the centimeter per second. And what is shown over here is a box. So if I put over a color, so if I do the echo of this baby, you will see some color is coming over here. Blue color or the red color, whatever it is. So blue color and the red color, we know the mnemonic BART, which Dr. Sajan has told you. The blue away and the red towards. Fine. Whatever is shown, I'm not showing you the images. Whatever is shown, it is like this. Fine. Never press this button invert, because invert means whatever is red, it will become blue, and whatever blue will become red. So don't press this button invert. Rest the scales you can change. You can hide this scales and the color. You can show the colors, because you are using for the colors. It means color is required. Then high scale or the low scale. So this is 20. So it is now low. It is a medium. It's 45 and the high is 78. I can change the pulse repetition frequencies from here, which again Dr. Sajan told you. This how you change the pulse repetition frequencies. You can keep on decreasing the scales slowly. Okay. So these are the color modes. Then there is a Doppler mode. Once I press the Doppler mode, what I see over here is a pulse wave Doppler, and this is the range gate of the pulse wave Doppler, PW. It is written PW over here. And this is, yeah, you can see this pulse wave written over here. And this is the +2. +2 means this is the angle. You can change the angle over here. Now this is +60. You can see a line is coming over here. Angle of insonation, -60. So it has only 3 measurements: +60, -60, and 0 and 10. And you can increase or decrease the depth of this range gauge. So this is 5, 6, 7. So maximum 7 I can change if I have a bigger diameter to be done, and if it's smaller, then it is minimum is 1. Fine. So if I press it, now I press the button update. Now show. Now if I press this button update, what will happen on the screen is this is a Doppler which is coming, a baseline, up, and the below. Up means towards the probe, and below means away from the probe. Fine. I'm not showing you what is seen, but this is how it will be shown in the screen. Okay. Coming now, if I press the button 2D, it will come back to the 2D mode. Clear? Okay. Now, once we know the 2D, we know the color, we know Doppler, then is the M mode. If I press M mode, a line will come over here, which is almost a straight line. And sir will show you all the there's views. I'm not showing the views. So what we are doing over here is a measurement. And if I want to calculate something like ejection fraction or a LA ratio, I have to press again the update, and I see there is some contraction going on. So I can use the word calipers and measure the values over here. So again, this will be shown when we learn about the ejection fraction. Yeah. So this is like a mitral valve moving. I am seeing how the left ventricle cavity is contracting and it is getting open up. So systole, diastole. So we calculate the ejection fraction over here. Clear? Okay. So that is about the M mode, and this is how we use the update button when you want both the images together. Every machine has its own setup, but this is the basics one. Fine. So now I'm coming from this to this side. So this was what we saw. This was the touchpad, or the joystick, whatever it is there. It can be like a rounded one, it can be square one, it can be bigger one, depending on the machine. And what I'm doing along with this is, once I'm doing this, what I do is I freeze it. And then I can use this touchpad and move the screens. So when I move this is like actually a movie. So you can see over here, just show over here. You can see 82. Once I move like this, 73, 74, 76. So these are all the pictures which have been collected and a movie has been made. Fine. And if I want to save this one picture, I'll press this button, save. If I want to move this, I press the clip button, then I will save everything, the whole image. So let's see. So let's save this clip. So I press this clip, I press this button, clip. So now what is happening is it has shown me a blue color and it has been saved. Now see again. Save twice. Fine. If I want to see this, luckily this baby has a, this baby has a PDA. I'm not showing the structure, but this baby has a PDA. And if I save this clip, again this blue color comes and this has been saved. If I put a Doppler over here, so it is, I think, let's do this baby. So what sir was telling you was aliasing. So what is happening? The peak is getting distorted and peak is coming down. So this is aliasing. So what I need to do is I need to go from 90 to higher velocities. So let's do that. So what I do is I increase the scale. So that was one thing, I increase the scale or I shift to continuous wave Doppler. You see, this is the velocity up. So this is the PDF which is moving and there's some diastolic disturbance which was happening in the pulmonary. So if I want to measure the velocity of this, I'll measure with the calipers. So this is 150. So the Dr. Mohit will teach you this part PDA. So when he will teach you, he'll tell you the velocity, how this velocity will differ from the PDA part. So luckily this baby had a PDA. I'm just showing you the PDA actually. Fine. Okay. Coming back to the this basics again. So this is how we use a freeze button, how we use a select button. So select button is used to move that cursor, calipers to measure these things, calculators. So if I want to measure the calculations, do the calculations. So if the machine knows that, I press freeze it and press the calculations, it will show me some basic calculations over here, which are already done in this. So if I'm in the Plex view, the machine knows that I'm in the Plex view. So they know I have to measure the LV cavity, LA ratio, area, LV volume, LV mass. So they know I am in the LV cavity. So machine is intelligent and it tells you that I am in the LV cavity. Once I press the LV, it comes as LV diastole and LV systole. And once I do this, it will show me the ejection fraction. Okay. So this is how we use the calculators, the calipers, the select button, the click button, the save button, and the freeze button. Okay. So now coming to the depth image optimization. So once you see this image, now what I'll do is I'll decrease the depth. Decrease the depth means I'll see a bigger view. I'm not seeing at the depth, I'm seeing the superficial structure. I increase it more. What you are seeing is actually nothing. So the image optimization is very important. So now you are seeing some heart, left ventricle, right ventricle, the left atrium, this is the mitral valve, this aortic valve, and aortic outlet. So I decrease it further. Now you get a better image. So you are seeing almost this total image, and 66 to 70% of it is covered with the image. 66 to 70% is covered with the image, which means that this is important. And like, unfortunately, light has gone and we are on the UPS, so it is working still. Fine. Okay. So this is the important thing. So this I have done with a total of how much? 66% of the images covering this total screen. So this is depth. So if I decrease it this much, this is not good. This is not good. I'm not able to see it. I don't want this. This is unnecessary. And if I increase it, now this is the right path. Okay, so this is how we use the depth. Then there is something zoom. Zoom means this part will be zoomed. I'll lose some pixels, but I'll get a bigger image of that part. Okay, so that is how the zoom button works. But zoom is rarely used. We use the depth button. Then the important is, then another important is a gain. Again, can you वो बंद कर सकते हो light. I'm just switching off the light. Yeah, good. So now you will see what a gain means. So this is the overall gain. I'm pressing, this is the gain button. Now this is totally black. You don't see the structures. You are not seeing the structures. This is totally black. This is not good. Now if I'm increasing the gain, which means actually the brightness, this is totally white. Is it good? No. Again, no. So it has to be optimal gain. So you have a button which is known as eye scan or the auto gain. Once you press this eye scan, I'm pressing it. Yeah, I'm pressing it. So the intelligent machine already knows how to use that auto gain. But if I want, I can divide this into two in this machine, but otherwise there is something which is not time gain composition, and you can use it for 8 parts. So you can divide this into 8, 1, 2, 3, 4, 5, 6, 7, 8. But in this machine, there are only 2. So this is divided into half. And what I'm doing is decreasing the gain in the upper part, but the lower part is still left. So if I go back again, auto gain. Now I decrease in the lower part, and the upper part is still there. Fine. So this is, I have kept the gain same for this, but this gain has decreased. I want to go back, auto gain. So you reach there. Fine. I hope you know how the gain buttons, the depth buttons, the auto gain buttons, this touchpad, everything, and this modes, update, and the QWERTY keyboard. If you want to label it, this part, so you press the text and you can write everything, whatever you want to write. This is the right ventricle inside it, right ventricle, and save it. And save it. Once you press save, so it is saved already into that one. Fine. So, okay. So this is because I showed you the screen, this. Now I come to the probes. So this is the probe which I'm using for this baby. So this is the piezoelectric crystals where there are there. This is the point indicator, which we call as the indicator. And this point indicator corresponds to whatever is there, a dot in this. Find the probe indicator is the dot which is over shown, which is shown over here. So I can change this dot to other side also. Fine. So once I press the 2D, this you can see this dot is corresponding here. So I can change this dot, the probe indicator this side. I can change it to lower right and the lower left. So this is the upper right. You can see UR, upper right, upper left, down left, and then down right. Fine. So again this. So by convention, for all echocardiographies, we keep it on the left side. And for all other this examination, so like if I want to use this button, the ultrasound. So once I press the exam button, I want to go to the neonatal. So automatically it changes to the other side, to the right side, because the machine is tuned like this. And I can use for the cranial ultrasound. Fine. So now I optimize the image. So now I optimize the image. Clear? So this is what I'm getting over here. So cranial ultrasound. Fine. Same thing I can do in the abdomen. And if I press the abdomen button, so now it comes back on this side. So it is abdomen is. So I can see the kidney part. I can see the structure. So whatever you're looking for, you can see over there. Clear? So this is just I want to tell, like you can see the liver. So this is liver, porta, patis, and everything is seen. Okay. So we are not going into detail of the structures. Okay. So now this probe indicator, I have told you that probe indicator keeps on changing. We can change according to this. And this is the piezoelectric crystal where they're stored. This is the housing body, and this is the whole is a relief, probe relief. So, and if I can use it this way so that there is no strain on my hand. I can use this way, so there is no strain on my hand. And this is attached to this machine in the channel. See that? See that? So I can open from here. and then show you this is where it is attached. And wherever it is attached, you can see it is written 4 to 8 megahertz. This is the name of the probe P10X, 8 to 4 megahertz. So this is being used from 4 to 8 megahertz frequency. So Dr. Sajna has told you what is the frequency and what is the wavelength. So this is 4 to 8 megahertz. So it will be used for a newborn heart. So I put it back over here. Fine. So the other probe is the other probe is the other probe is I have the from 6 to 30 megahertz. So that was the probe which was the basic one which we use for the newborns, which we call a thumbprint probe. So you can see these two probes. This is thumbprint probe or the phased array probe which we have, and this is a linear probe. The crystals, this is the arrangement of the crystals. So the crystal arranged in a linear fashion over here, and for this they are arranged in a sequence up. So it sends into the phased manner. In the linear, they send just a linear. So I'll show you one image of the. Oh, sorry. So this is actually the probe extender. You need to actually get along with the machine. Some companies don't give it, some companies give it. Sorry. We need to clean the probe. Okay. We clean the probe with a chlorhexidine or isopropyl alcohol. Just one part, this one. Right. So then, depending on the preterm baby, so ideally you should preheat the jelly, and then I'm putting the lung ultrasound. You can see. So this is the linear arrangement of the array in this probe, the piezoelectric crystal, and you can get image like a square or a rectangle, you can see. So this is what we are skin. This is a pleural line. We'll teach you this all this in pleural line and then the first thing. So this is how the probe can show you the different views, and depending on that you get the images. So fine, if I put an M mode over here, so I get again the line. The things remain the same depending on the structure. So I'm getting a C short sign again. You will teach you in this lung ultrasound. Fine. So you now know the basics. You have to switch on the machine. I'm just repeating the things. You need to switch on the machine from the keep it in the UPS mode. Then once it is on, you get this screen. On the screen, you will get something that is basically where you will get all the images seen. You can store the images from here. All these things are shown over here, and you can use these buttons. Fine. And then once you go to this, so you have 2D mode, color mode, Doppler mode, M mode. Update is when you use the two things together. Then this is the touchpad, the freeze button, the save, the clip, the save calculations, whatever you have done, the select. Then the calipers, the calculators, the depth, the gain. These are three of the gain buttons, but you can have many gain buttons over there, depending on how you divide them, the screen. Then you have the probes, different probes. We saw the phase array probes. We saw the linear probes. There are hockey stick probes. Many other probes are there, which Dr. Sajna has shown you. And then you can store the image. Like we have saved this images. Now I can go back to this review image. So I get save the file. So this was once I saved. This was which I saved for the PDA part. Now you can review this thing, and you can always do the calculations over here. You can transfer them to your pen drive. You can transfer them directly. So this is what we have done. So once I freeze it, I can see this images. Fine. Any questions till now? If I have missed out something, sir, Dr. Mohit, sir. Hello. Mohit, sir. मेरा phone
Sir, Mohit sir is coming in 2 minutes.
Okay. So any questions still for this?
Any questions in chat box?
So anything missed, because they have listened to the Dr. Sargent's lecture, so we can have in the chat box if you want to see something missed or the practical thing which you want to know. We didn't go into the calculations part. We just stayed on the machine, the probes, and this side. Vilas, any questions in the chat box?
No, sir. No questions.
No questions. So it means no question. Either not interested or they know too much.
Sir, there is one question in chat box. Can we wipe the probe with sterilium or with spirit? Sir, your voice is breaking. Sir, your voice is not coming clearly.
That, yeah. Is it better now?
Yes, sir.
Okay. So yes, you can use isopropyl alcohol for this, cleaning this probe. 70% isopropyl alcohol.
Sir, no further.
Nobody asked me how to print the image.
So
Can I demonstrate taking measurements? Okay. Yes, I can demonstrate, but before that, you should know the image. So I can definitely do that for you. Yeah, sir. So you have a jelly, you use this probe. So what I'm doing is I'm not showing you the views there. I'm just showing you how to do the calculations. So I'm on the abdomen. I need to change this exam and I want to go to the cardiac because that is basically tuned for this. Okay. I use the auto gain button. I can slightly increase the gain for you. Then I press, like you want to do the ejection fraction or you want to do the LA ratio. I think you want to do the LA ratio because we saw the PDA. So I press the M mode. Now what I'm getting the two images here is this center one is the aorta and this is the LA. So if you want to measure this LA ratio, what I can do is I can press the calculator button and already I have the AO and the LA. So what I do is I press the AO. Sorry. Okay. So I press the AO first and I take the measurement. I got the 0.63. I save it. Then I press the another one, the LA, select it. So the biggest measurement of the LA. I save it. So I got 1.32 by 0.63. So it is almost 2. It is almost 2. So the LA ratio is 2. This is how you take the measurements over there. If there are already preset calculations, it will be easy for you. Otherwise, it can take time. So if I want to measure the, for example, if I want to measure the PDA size, so I press I locate this. So now for you, I'm putting the color and showing you where actually I should measure the PDA size. But again, this will be taught by sir to you. So I see the whole image. So I can measure the minimized point where actually it is opening into the pulmonary. So I'm just showing you the example. So again, for this, the calipers. Sorry. I hide it. the colors. It should not be taken the color part. So then you can use this two parts. Almost 2.5 millimeters. Fine. So this is just an example to show how you do it, but I'm not optimizing the image and everything. So will the probe not get damaged on cleaning with isoprobe? No, no, no. It is already covered. It has a lens. Sir must have shown you that part. Dr. Sarjan sir, there is a actually lens which covers it. It doesn't get damaged. The piezoelectric crystal doesn't get damaged. You can easily clean it. We have been using this probe since last 11 years. Till date, even if you throw it, it will not get damaged. Don't throw it, but that's what the company claims. Dr. Mohit can tell you better maybe in this part, but this is how we do it. Any other question, Vilas?
No, sir, no questions.
I finished my session on time so that we have more time for the questions. This is not a theory. This is, you can ask anything actually.
Welcome Dr. Mohit Sahni, sir, for the next session. He is a director of neonatal focus eco, NAFCO Academy Surat, and senior neonatologist at Surat Kids Hospital. He will take a class on basic of eco, views for neonatologist. Sir was editor-in-chief in Journal of Neonatology, India, from 2017 to 22. He was a president NNF, Gujarat State Branch 2020 to 2021. He was a governing body member, NNF Western Zone, 2017 and 18. He was a member of Neonatal COVID Task Force, Government of India, and editor-in-chief of Point of Care Neonatal Ultrasound and Echo, and also Neonatal Apical Medici. Welcome, sir.
Thank you, Dr. Vilas. Thank you very much. And I would like to thank the whole organizing team of Guj NeoCon and West Zone NeoCon 2024. So it's really great to be with you all. So now these sessions, what we will do is we will now start with echo, the general principles of the ultrasonography and that of head ultrasound, lung ultrasound. Those principles remain same and they are static for all the types of ultrasonographies, whether it is head ultrasound or the lung ultrasound. But in echo is one of the major part. So we will, in this workshop, we will just concentrate mainly on our normal views, whether it is echo, whether it is head ultrasound, whether it is lung ultrasound. So my presentation will be divided in these three things. So the first thing is, before we are going to do the echo for the heart, we should be well aware of the heart orientation in the baby's chest and its surfaces and border. So in short, we will discuss that. Then we will discuss various windows from where we acquire those views. And then we will see what type of views we see on the machine's screen of the machine. And then what are the various structures that we see in those views. So these are the three parts, major parts of my presentation. So the first disclaimer for everyone is, like, if you are doing the functional echo, so it is more in the the area. This area is mainly being concerned with pediatric cardiologists. So if you are as a neonatologist or as a pediatric intensivist or intensivist or pediatrician, if we are doing echo and if I detect the congenital heart disease, please, if you have any doubt regarding any congenital issues, please don't forget to involve the pediatric cardiologist for at least one echo to diagnose that. Otherwise, sometimes it can be a legal issues. So that is the disclaimer I want to bring about in front of you. So now this is the normal heart orientation. This is how the heart will be lying. So this is the most anterior surface, or what we call as the sternocostal surface. So as you all must be knowing, this sternocostal surface, this one here, this part is mainly found by the right ventricle. This is the right ventricle. Okay. So this is your right ventricle, and that's why this pulmonary artery is arising from it and it's getting bifurcated. So this is the sternocostal surface, which is formed by the right ventricle. Now, if we go towards the left, this left side, so this is the left border, and here it will be formed by your LV, left ventricle. This one is your left atrium, and this is your left atrial appendage. So this is your left atrial appendage. This is left atrium. As you can see, these two are the pulmonary veins, and this left border is being formed by the left ventricle. And as you will be seeing, this is your anterior surface and this is your posterior surface. So you can see the most anterior chamber of the heart is your right ventricle. And then the posterior chamber is your left ventricle. So this is how the orientation is. So as you can see in this animation, so what we have discussed till now the sternocostal surface, left border of the heart. Okay. And now we will move and go and see the right border of the heart. The right border of the heart. It will move. The heart will move towards the right border. Yes. So it is moving. I will pause it here. Take out these labeling. Okay. Now you can see very well. No need to label also. This is what is. Can anybody write in the chat pod what is this chamber is? I have already told you 2 chambers. Now it is your turn. I just want to see how much attentive everybody is. Yes, somebody has written. Yes, great. So this is your RA, right atrium. Very nice. And what is this A and what is B? Can you write in the chat box? What is A and what is B? Yeah, SVC and IVC. Very nice. Thank you. So that is good. So, so this is your right border and this is your RA. This is your SVC. This is your IVC. Okay. And now I will just show you the orientation of aorta. See, the aorta is arising from LV. This is, and then it is posteriorly, it is going behind the pulmonary artery. From the LV, the aorta is arising and moving behind like this. These are the 3 branches. This is ascending aorta. This is the transverse aorta. And now this is the descending aorta. And anterior and right angle to aorta is your pulmonary artery here. Sorry. Yeah, here. So this is your pulmonary artery, which is anterior and right angle to the aorta. Okay. And now here you see, this is a pulmonary artery, and above this is rounding down, is encircling the pulmonary artery. This is aorta. Aorta is encircling the pulmonary artery, and then you have 2 branches of pulmonary artery. One is right pulmonary artery and one is left pulmonary artery. I hope, yeah, you are seeing from the posterior border. Now this is a posterior border, and you see this is divided RPA and LPA, and encircling is the aorta. And anybody can tell what is this chamber? This one? This chamber. What is this chamber? LA. Very nice. So this is your left atrium. Great. And these are the 4 pulmonary veins entering into your LA. Okay. Now the only thing which is left is your inferior or diaphragmatic surface. We will see that. And that is mainly, this is a surface on which the heart rests in diaphragm. And this is mainly being formed by the LV, left ventricle. Why it is not moving? Yeah, sorry. So this is your formed by the left ventricle. Great. Okay. So this is the orientation of the heart. Okay. Now, everybody is clear about the orientation of the various surface and borders of the heart, because that will be important when we talk about the views. And now, how the heart is lying in the baby's chest. So this is a newborn baby, and this is how slantingly the heart is lying in the baby's chest. In adults, the heart is more vertical. In newborns, the heart is more slanting, like this. Okay. So when we put the probe, so this is the probe. When we put the probe like this, in adult, it will be upright, but in newborns, you have to bring it lateral to get the upright of the heart. So this is for the apical view, because the heart is lying more slanting in the baby's chest. Is it clear, everyone? I hope it should be clear. Okay. So now let's talk about the various windows on the baby's chest. So before that, we should be well aware of the various landmarks on the baby's chest. So this is your nipple, and this is your nipple line. Then we have the sternum. This is sternum. Below the nipple line, that is 1/3 of the sternum, is the lower 1/3 of the sternum. And then above the nipple line is the 2/3 part of the sternum. And this is your xiphisternum. Then we have suprasternal notch. Then these are the right and left clavicles. So this is very obvious. So when we talk about various windows, the first of them is the apical window. So apical window is the area just below the nipple in the mid clavicular line. This apical window we use for the apical 4-chamber, 5-chamber, and we also call it 6-chamber or pulmonary trunk crisscross view. So we use apical window for apical 4-chamber, 5-chamber, and 6-chamber. And then we do the parasternal. We have the parasternal windows. See, all these windows, they were formed, imagined on the baby's chest by the people who started doing an echo initially. And with their experience, they found that those particular views are best seen in these windows, and they formulated these windows. So the parasternal windows are further divided into two. A is low parasternal windows. So for this, we put the probe in the lower 1/3 of the sternum, that is at the nipple line. And then we have the high parasternal windows, which is in the upper 2/3 of the sternum. That is just upper 1/3 of the sternum, in fact. So that is just below the clavicle, and we also call them subclavicular areas. In low parasternal windows, we have two views, two windows. In those low parasternal windows, we have two views. One is parasternal long axis view that cuts the heart in longitudinal, and then parasternal short axis view that cuts the heart in short axis. In high parasternal views, we will have from suprasternal notch and the right subclavicular area, we have the arch view. Then we have this SVC Doppler view. And then from the left subclavicular area, we have ductal view, pulmonary artery view, pulmonary vein view. And then below there, in the left side of the sternum, we have the SVC diameter view. In today, this is the basic workshop. So we will be discussing parasternal long axis. We will be discussing parasternal short axis. We will be discussing arch view, ductal view, pulmonary vein artery view, and pulmonary vein view. So instead of these 9 views, that is basically we discuss all the 9 views in the longer courses or in the advanced workshop. In the basic workshop, we discuss 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, and 2, 6. 6 views. Parasternal long axis, short axis, arch view, ductal view, pulmonary artery view, and pulmonary vein view. These 6 views we will discuss today. So this is your low parasternal window, that is at the nipple line, in the lower 1/3 of the sternum. So in this, we have plaques view and parasternal short axis and parasternal long axis view. Then we have high parasternal windows. In high parasternal window, that is in the upper 1/3 of the sternum, either on the left side of the sternum or on the right side of the sternum. We also call them subclavicular windows. We will today, in this, we will discuss aortic arch view, ductal view, that is PDA view, pulmonary artery view, and pulmonary vein view. These 4 views in the high parasternal group we will discuss today. This suprasternal notch is in pediatric and adult. this area is being used to look for the arch view. But in newborns, if you are practicing neonatology, you must have seen, especially in the babies who are on CPAP and ventilator, this notch itself, especially in the preterm babies, is very small. And then it is very difficult to extend the neck. And to put the probe in the suprasternal notch is a challenge. So that's why we do the arch view from the right subclavicular area, this area. We will show you how we will do it. This is how we use that. So that's why we can ignore suprasternal notch view from where we do the arch view that we do in pediatric or adult. And then we, in the end, we have subcostal views. And in neonatology, we tend to do the subcostal views in the last, because if the babies are not sedated or they are not on the ventilator, they are awake or on their own when they are respiring, it is irritating for them and they start crying. So in subcostal views, we have cross-sectional views and longitudinal views. The cross-sectional views are basically the three: the situs view, atrial view, and the SVC Doppler view. Today, we will discuss the situs view and the atrial view in the cross-sectional subcostal window. And then in longitudinal, we will discuss IVC view, that is inferior vena cava view, and the abdominal aorta view. So these are the four things we will discuss in subcostal windows. Okay, and this is the subcostal area window just below the xiphisternum here. So area between xiphisternum and the umbilicus. So as I discussed, we will discuss the situs view, atrial view, IVC, and the abdominal aorta. These four things we will discuss today in this workshop. So in the end, just the synopsis: apical view, low parasternal view, high parasternal views, and the subcostal views: apical, high parasternal, suprasternal, low parasternal, and subcostal. So these are the windows that we commonly use to get the various views of the heart. Before we go for the views, I always tell people to imagine a clock in front of the baby, so that why it happens, as it has been shown by Dr. Kamal, that on the probe we have the probe marker. I will discuss that. And then it always corresponds to the probe orientation marker on the screen. So that's why the probe marker always moves here and there. So instead of remembering it right, left, up, down, we remember in terms of a clock. So 12 o'clock is at the head, 6 o'clock towards the foot, 3 o'clock towards the left side, 9 o'clock is towards the right side. And this is what I was telling. This is the probe marker. It corresponds to this probe orientation marker. And Dr. Kamal already told this probe orientation marker, by convention in cardiology, is always on the left side of the screen. This always remains on the left side of the screen. The only thing we do on cardiology is we either move it up or down, but it always remains on the left side of the screen. And suppose suppose this is the baby's chest. Okay, this is the baby's chest. This is right, this is left. Okay, now I've kept a probe here, and the probe marker is here, is facing here. Okay, and these are the chambers. So if anybody please can write in the chat box, what is chamber 1, 2, 3, and 4? The probe, this is the probe. This is a probe marker facing here, and you are doing this view. So what are these chambers 1, 2, 3, and 4? If you can write in the chat box. Very nice. LALB, RARB, very good. Nice. Now suppose what happens is, now this is the probe, and now your probe marker is pointing here. Now this is the probe marker pointing here. Now you can label which is what is chamber 1, 2, 3, and 4, please. Yeah, so this is Dr. Abdul, we will discuss. So that comes under the category of this thing, anatomical issues, anatomical things. We will discuss that. First, we are just discussing the orientation of marker, and Dr. Arvind has rightly written one now is RA, RV, LA, and LB. Very nice. Great. So that means this is the orientation is as per where this probe marker is facing, because this probe orientation marker is fixed. Okay. So you understood this. Good. So now you see, before moving ahead for the views, now the first thing you should know is, so this is your probe. And from probe, this is how the ultrasonic waves, they come out. Here is the probe marker. And this is where what you will see on the screen is your probe orientation marker. They corresponds. Okay. So we should understand the movement of the probe. And whatever movement I will be discussing is always with respect to the foot of the probe. This is your foot of the probe. Okay. When the probe moves like this, ultrasonic waves moves like this, as I was showing. When we keep the probe here on the baby surface, see, I am moving the probe up and down. Down, up is anterior, down, behind, down is, this is posterior. So this movement is known as sweeping movement or the tilting movement. Sweeping movement or the tilting movement. So this is sweep or tilt. This always with respect to the probe, and this is rotation. I'm just moving around the vertical axis, rotation. And if I move it like this, it is angulation. So you should be well aware of the sweeping or the tilting movement that I've shown. Sweeping upwards is anteriorly, sweeping downwards is posteriorly, that I've shown you. Now let us discuss the screen. This is the echo screen. Here what you're seeing is the organ of the interest. In our case, it is heart. So this is heart. Then this is a color window. This is velocity scale. All this has been clearly in detail discussed by Dr. Kamal. So I won't go to detail, and this you have already know. Red is towards the probe and blue is away from the probe. But so we directly go to the basic views. Whichever window we use for the various views, we do it under three categories. One is 2D. So this is 2D. Then we do the Doppler. Dopplers are of three types: color Doppler, pulse wave Doppler, and continuous wave Doppler. And then we do M mode, that is the motion mode. Dr. Sajan has clearly explained what is motion mode. So that is basically we use to do the measurement of the various structures. Okay. So, and the functioning of the heart by assessing the size of the various chambers of the heart. Mainly the chambers what we use to assess the size is LV, RV, and LA. So first we will start with the apical 4-chamber views. So for now onwards, I would request everyone to first concentrate on this part of your screen. There will be a video that how and where to keep the probe. Then you concentrate on this part of the screen where you will see the video of the structure, and here you will see the labeled structures of that particular view. So there will be 3 parts of the screen, and you watch the screen like that. So this is a apical view. We put the probe at the apical window as I showed you, and pointer is pointing at 2 to 3 o'clock position, that is towards the left shoulder. In here you can see the probe orientation marker is down because we want to see the heart upright. So this is anatomically corrected upright heart. So this is probe orientation marker. Probe marker is pointing at 2 to 3 o'clock position, that is towards the left side. So this is your LA, LV. This is mitral valve. RA, RV. This is tricuspid valve. This is your interatrial septum. This is your interventricular septum. This thing you are seeing here is your descending aorta. As it wraps around the heart, so when the heart is being cut longitudinally, this is being seen in cross section. And this is 1, 2, and 3. These are the 3 pulmonary veins you are seeing entering into LA. So these are the structures you will see in a apical 4-chamber view. This is how, this is a probe. This is how the ultrasonic waves are going out, and they cut the heart like this. and bring this apical 4-chamber view in front of you like this. So when we do the Dopplers, so I'm doing the Dopplers across the mitral valve. Here is your probe. So the blood flowing from RA to RV is red. And if I want to see the TR jet will be the blood flowing from RV to RA, and it will be blue because it is moving away from the probe. Similarly, I am doing now the Dopplers across the mitral valve. The blood flowing from LA to LV will be red because it is towards the probe. And if there is MR, if I see the MR will be blue because that will be the blood flowing from LV to LA. And now we do the apical 5-chamber view. So a 5-chamber view is what you see this. What I did, I sweep the probe anteriorly. When I sweep the probe anteriorly, the foot of the probe, this 5th chamber opens up, and this is your aorta. And this is your aortic valve here. So this is your LA, LV, aorta, aortic valve, RA, RV. So this is apical 5-chamber view. We use it to calculate the velocity of the blood flowing through the aorta like this. Okay, so this is the blood flowing in the aorta, and you can see it is blue because it is moving away from the probe. That's why it is blue. This red jet is the blood flowing from LA to LV. It is red because it is moving towards the probe, because the blood is traveling from left atria to left ventricle towards the probe. And in this aorta, you see the blood is traveling from LV outwards, outside. So that's why it is blue, because it is away from the probe. And now again, you see, I sweep the probe further anteriorly, upwards. So what you see is, there was aorta which was like this, it is gone, and perpendicular to this and anterior to that, another vessel has come up. So this is your pulmonary trunk, and this is your pulmonary valve, pulmonary trunk and pulmonary valve. I will show you how that in this animation. So now see this is heart which is being cut. This is your LA, mitral valve, and LV. This is RA, tricuspid valve, and RV. Now, if I move anterior to the cavity of LV, you can see this is the cavity of LV, and anterior to that, this is your aorta. So that is your apical 5-chamber view. That's why when we sweep the probe anteriorly, you see the aorta 5-chamber view, and this aorta is going like this, up like this. Now, if I move the probe more anterior to this, so you will see anterior to this aorta is this vessel, that is your pulmonary artery, and very well you can see it is anterior and right angle. So that's why when I went from 5-chamber view to 6-chamber view, you stopped seeing this aorta and you started seeing the pulmonary artery right angle to that. So this is your pulmonary trunk crisscross. So now with this animation, it's clear that the cavity of left ventricle is posterior. Anterior to that is the aorta, and anterior to aorta is pulmonary artery and right angle to the aorta. So that's why you see apical 4-chamber, 5-chamber, and 6-chamber views. So those are your apical views. Now we come down to the low parasternal views. In low parasternal views, first we discuss the parasternal long axis view, in which the ultrasonic beams cut the heart in longitudinally. So where we keep the probe at the nipple line, pointer pointing at 11 o'clock position. 11 o'clock means right shoulder. And here you can see probe orientation marker is now up here. Only for apical 4-chamber view, it is down here. For rest of the views, it is up here. And now you see the heart is being cut longitudinally. And we have already discussed the most anterior part of the heart is RV. So this is your RV. This is interventricular septum. This is your LV, mitral valve, LA, and this is aorta and aortic valve. So this is the heart which is being cut in longitudinal section. You can see in this animation, this is the probe on the baby's chest. In animation, it is, and this pointer is pointing at 11 o'clock. Now let this baby lie. Yeah. So it cuts the heart longitudinally like this. So this is your RV, LV, aorta, aortic valve, mitral valve, and LA, left atrium. And this is how the heart is being cut in a longitudinal section. And now I'm trying to do the Dopplers for the interventricular septum. Then in this also there are two sweeps. Now what you are seeing in this, I am sweeping the probe down towards the foot of the baby. You get to see the tricuspid valve. So this is your tricuspid valve sweep. This is tricuspid valve. And now I sweep the probe up towards the head of the baby, towards the head. Now you see this aorta will be gone. And when you sweep the probe up, this vertically you will see the vessel coming from above down, and it is dividing into two. You can say in two parts. So this is your MPA, main pulmonary artery. These are the pulmonary valves, and this is how it is dividing. So this is your MPA, this is RPA, this is LPA. So you see this, when I sweep it up, your aorta, which was horizontal, is gone, and vertical to that from above, the pulmonary artery is coming down. So this is your pulmonary artery sweep. This is C. When I sweep the probe up, this is what you see. The aorta in parasternal long axis view is gone, and this is your pulmonary artery sweep and pulmonary artery. When I sweep, and this is the color Dopplers I'm doing in the pulmonary artery. And when I sweep the probe down towards the right hip, this is your tricuspid valve sweep. So these are the two sweeps we do in parasternal long axis view. So I'm doing the color Doppler, and the TR jet here also will be blue because the blood is moving from RV to RA, and here is your probe. So it will be moving away from the probe. That's why it will be blue. This here you concentrate here. This is red flow, RA to RV, RA to RV, RA to RV, red flow. And now you see this blue flow from the tricuspid valve. So this is your TR jet. So now we go to parasternal short axis view. So here you can see I am rotating the probe from 11 o'clock to 1 o'clock, exact 90 degree, 11 o'clock to 1 o'clock. It will cut the heart in cross section. So here I showed you in heart orientation, this is a place where there is a base of the heart. Base of the heart is the junction between atria and ventricles. So that is the place from where the aorta starts. So what we call as the root of aorta. So it cuts the heart in cross section at the root of the aorta. And this is what you will see in the center. This is your root of the aorta. And these things here is the tricuspid. These are the cusp of aortic valve. So it looks like a Mercedes-Benz. So that's why it is known as Mercedes-Benz sign view. Here, you see this. This is your aorta. And then you have these cusps of aorta like this. So this will be Mercedes-Benz sign view. So this is known as Mercedes-Benz sign view. So this is your root of aorta, pulmonary artery, pulmonary valve. This is your RV, right ventricle. This is tricuspid valve. This is RA, right atrium. This is LA, left atrium. And this is interatrial septum. So this is known as Mercedes-Benz sign view. Okay. So because it is heart is being cut in cross section at the root of the aorta. This is how it is being cut. And then we sweep the probe. This is the base of the heart. This is the root of aorta. This is the base of the heart. That means the junction of atria and the ventricles. We sweep the probe from the base of the heart towards the apex of the heart. So when I enter from the base of the heart towards the apex of the heart through LV, the next structure I will pass will be your mitral valve. Here you see this sweeping movement of the probe. From the base of the heart, it's towards the apex of the heart, like this. After the Mercedes-Benz view, I see the mitral valve view, and this is like a fish mouth, so it is known as fish mouth view. So this is your interventricular septum. This is your LV cavity. This is the mitral valve, and this is the RV cavity. So this is fish mouth view or mitral valve view. The next thing, when I sweep down towards the apex, I will encounter papillary muscle. So this is known as the papillary muscle view. This is LV, papillary muscles, interventricular septum, and this is your RV, right ventricle cavity. And then in the end, when we take the probe till apex, we see that which is the apex forming chamber. In normal heart, the apex forming chamber is always LV. Only in hypoplastic left heart, the apex forming chamber will be RV. So this is, you can see the RV cavity will become very small and the apex is formed by the LV. Okay, so that is your low parasternal views, in which we discuss parasternal long axis view and parasternal short axis view. The next is your high parasternal views. And as I told you, it is mostly in the upper 1/3 of the sternum. On the right side of the sternum, where there is a right clavicle, we have this right parasternal, high parasternal views or right subclavicular views. And on the left side of the sternum, that is below the left clavicle, we have left subclavicular or left high parasternal views. On the right side, we will discuss, we will not discuss this SVC Doppler view. This is basically for the advanced ones. So we will discuss the arch view. And from the left subclavicular area, we will discuss these three views: ductal view, pulmonary artery view, and pulmonary vein view. And again, I told you the arch view we don't do in newborns from the suprasternal notch. And this view also we will not discuss. That is the SVC diameter view. So we will be seeing arch view, ductal view, pulmonary artery view, and pulmonary vein view. So see, I kept the probe in the right subclavicular area, pointer pointing at 12 to 1 o'clock position. And this is how you see the arch view. This is ascending aorta, isthmus of the aorta, 1, 2, and 3 branches. And this is the descending aorta. And as I showed you in the animation of the heart, how the heart orientation is. So pulmonary artery bifurcates and it is right angle to the aorta. That's why this is your RPA looking in the cross-sectional view. So this is arch of aorta and this is your RPA, right pulmonary artery. I am doing the color Dopplers of the, putting the color window on the aorta. That is your arch view. And then the ductal view, that is a PDA view that we do from the left subclavicular area on the left side of the sternum. Again, the pointer is pointing at 12 to 1 o'clock position. We mainly see two structures. One is, this is pulmonary artery and this one is descending aorta. So this is your pulmonary artery and this is your descending aorta. And the PDA is what? PDA is a connection between aorta and the pulmonary artery. Okay. Now you see, this is pulmonary artery, this is descending aorta. Two are blue. Why blue? Because the blood is flowing away from the probe. Now, if you have a duct, a connection between this descending aorta and pulmonary artery like this, okay, and the blood is flowing from descending aorta, from this descending aorta towards the pulmonary artery like this, through the duct. What will be the color of the blood flow for everyone? You can write in the chat box. If the blood through the PDA, this connection between descending aorta and pulmonary artery, is flowing from aorta towards pulmonary artery, that means left to right, what will be the color? Let me see, red, red, red. Yes, it will be red, not blue. Why? Here is your probe. And the blood is flowing from aorta towards the pulmonary arteries, that is towards the probe. As it is towards the probe, it will be red. If it is right to left, that is from the pulmonary artery and going towards the aorta, it will be away from the probe. And then in that case, it will be blue. So left to right flows are always red and right to left flows are always blue. Okay, so remember this. And now you can see there is the actual PDA. From descending aorta to pulmonary artery, it is flowing left to right. So that's why it is, you can see it is red. Then we have pulmonary artery view. For this, again, it is done from the left subclavicular area on the left side of the sternum. But in this, the pointer is pointing at 3 o'clock. And you see this structure. So this is your MPA, RPA, LPA. So this is your pulmonary artery, which is seeing as bifurcation. This is a cross-section seen, that is cross-section of aorta. So this is aorta. And this cross-section here is SVC. So SVC is most right, then comes the ascending aorta, then comes the pulmonary artery, and after the pulmonary artery, that is towards the left of the pulmonary artery, you will have descending aorta. And this view is also very important because aorta is always on the right and posterior to pulmonary artery. You see this. This is right, this is left. So aorta is always right, and this is your SVC. This is your pulmonary artery. This is anterior because here is your probe. So this is anterior. This is posterior. You see this border. Pulmonary artery is anterior to this aorta. So the position of aorta in this view is it is always on the right and posterior to pulmonary artery. Whenever this aorta is anterior or towards the left side of the pulmonary artery, then it is in that the condition is TGA, DTGA, transposition of great arteries. If the aorta is right and posterior, it is normal. If in this view aorta is anterior or towards the left of the pulmonary artery, it happens in DTGA. So that's why this view is good view to rule out TGA. This is the color we are doing for the pulmonary artery view. Then we keep the probe there in the left subclavicular area, pointer pointing at 3 o'clock. Okay. I just sweep the probe downwards. That is posterior. And I showed you that LA is posterior to pulmonary artery when we were showing the borders and surface of the heart in the animation. So posterior to pulmonary artery is your LA, and this is your LA. And then you see this 1, 2, 3, and 4. 4 pulmonary veins entering into LA. It will be more clear if I put a color. When we do this venous flow, we should be very careful about this velocity scale. Normally the arterial flow velocity scale, we keep it around 0.6 or 0.7 meters per second. But for pulmonary venous flow, we bring it down to the 0.3 meters per second. So as it is down, you can very well see this is the left lower. This blue is left upper. This is right lower, and here is the right upper. Upper ones will be blue because they are flowing away from the probe. The lower ones will be red because they are flowing towards the probe. So this is your pulmonary vein view, or also known as the crab view. So this is crab view or the pulmonary vein view. Then we come down to the subcostal views. In the subcostal views, we will, as I discussed with you, we will discuss the situs to determine the situs, whether the IVC is on the right, aorta is on the left, stomach shadow is on the left, and liver is on the right to maintain the situs. And then atrial view. And in longitudinal, we will discuss IVC and abdominal aorta view. So these view we will discuss. So this is for the situs. We put the probe in the just below the xiphisternum, and the probe orientation marker. The probe marker is pointing towards 3 o'clock. The marker is at 3 o'clock. And we keep the probe vertical to the skin surface. This is what we will see. Here is your right, here is your left. So you see on the right, this is the liver, and on left, this is the gastric shadow. This is the stomach shadow, this is liver. So it means your liver is on the right, gastric shadow is on the left, the situs is maintained. Then we see these two vessels. And when I press the probe, pinch the probe down, you can see this vessel does not get pinched, but this one in the liver gets pinched. So the one that pinches is IVC. So it is in the liver on the right side. The one that does not get pinched is towards left side, towards the stomach shadow side. So that means that is aorta. So aorta is on the left, IVC is on the right, liver is on the right, gastric shadow is on the left, situs is maintained, and the vessel's situs is also maintained. So that is how we determine the situs by the subcostal situs view. Then I bring this probe orientation marker again down. So this is from the situs view. It is the probe is still kept in the subcostal view, and the pointer is still pointing towards 3 o'clock. The only thing what I did was, for the situs view, the probe was vertical to the skin surface. But for this, I have swept the probe anteriorly. The probe is swept anteriorly. And then you start seeing, this is the right atria RA, this is LA, this is the interatrial septum, and this is here if there is a gap, and you see the flap like you see in here. This is the flap you are watching and seeing. If you see a flap and there is a gap in the interatrial septum, it is PFO. Okay. And I will skip this. And then now you see what I did. From 3 o'clock, I rotated the probe, and now the pointer is pointing at 12 o'clock. From 3 o'clock, it is pointing towards 12 o'clock. And I swept the probe towards the right because already I know the IVC is on the right side. So when I sweep the probe towards the right side of the baby, on the right side of the baby, I start seeing this IVC. So this is IVC passing through the liver, entering into RA, right atrium, and this is your hepatic vein. So this is your IVC view, like this. Probe is being kept, pointer is at 12 o'clock. Sweep the probe towards the right of the baby. This is how the ultrasonic waves will go. This is IVC through the liver, enters into RA here. And similarly, you saw this in 2D mode. This was the hepatic vein. So this is your IVC view. And now I sweep the probe towards the left side of the baby. Sweep the probe towards the left side of the baby. You start seeing this vertebrae, engorged vessel, and these are the two branches. So this is your abdominal aorta with celiac trunk and SMA. So this is your abdominal aorta view. So this is the various parameters that you will learn in PDA section, PPHN, and shock in the various sequences same. We do apical 4-chamber, 5-chamber, 6-chamber. Then low parasternal views, in which is divided into long axis, short axis. Then high parasternal views, in which we have the ductal view, arch view, pulmonary artery view, pulmonary vein view. And in the subcostal, we have atrial view, situs view, IVC and the abdominal aorta view. So thank you very much. If you have any questions, you can please ask. You can put it in the chat box and you can ask. So Vilas.
Yes, sir.
So my lecture
Sir,
is
there
over.
is a
Yeah, please.
yeah,
Please.
sir.
Yes, please.
So there was a one question: how to say which is LA or RA?
Yeah, so that is your anatomical this thing. So there are diagnostic features for RA and LA. For RA, we will see the bicaval view that I've skipped for this basic ultrasound workshop. So bicaval view, and then we look for station valve. So that will determine that the chamber is RA. And then on the positioning of valvular attachment for tricuspid valve and the moderator band will determine that that is RV. So that's how we determine RA and RV. So we do have Dr. Tushar. SVC view. SVC view is we have this. These are the specialized views. Intentionally, we skipped these views in the basic workshops, so that we always cover in the advanced workshops.
Sir, one more
Okay.
question.
Yes.
Sir, sir, can you explain the view for PDA?
Okay, I will just quickly show you the ductal view. Okay, then we will move on to Dr. Tushar. He is already logged in. So that is your high parasternal view. So where the pointer is being kept at, probe is being kept in the left subclavicular area, pointer pointing at 12 to 1 o'clock position. So you will get to see this. So you will get to see this. Ductal view. Ductal view is nothing, but you need to see the pulmonary artery and descending aorta. So you put a color. So this is how you will see the duct. So that is your ductal view. So the bicaval views and the situs inversus, we don't cover in the basic workshops. Okay, so that we cover in advance because otherwise it will take a lot of things. And this is a POCUS basic workshop. So that is covered in advance. So what I will do is I will also share a link in the group in which the whole lecture is there, in which that has been explained. So you can subscribe to NEFCO. In the end, I gave this. So all of you, what you can do is you can subscribe to NEFCO YouTube channel. There the lectures and links are there. So you can watch that. Yeah, sorry. Here. So NEFCO neonatal echo. This is a YouTube. So you people can search on the YouTube, write down NEFCO neonatal echoes, so that my channel will come. So you can subscribe to this channel. Situs inverters, it is a whole presentation. It is again covered in advanced ones. So that's why I've intentionally skipped. So I think so, Dr. Vilas, we will stop here because
Yes,
we have to cover 2 topics today. And another 2 topics. So Dr. Tushar is already there. So Dr. Tushar, are you there?
Yes, Dr. Mohit.
So
Good evening.
good
Good
evening,
evening,
Dr.
Dr.
Tushar.
Mohit. Good evening, Dr. Vilas and Dr. Kiran.
Good evening, sir. Good
Yeah,
evening.
and all the delegates.
So Dr. Tushar is a senior neonatologist. He did his DM. Yeah, Dr. Vilas, you can,
Yes, sir.
yes,
Yeah,
introduce,
sir.
please.
Sir, thank you for this great session as usual. It was a really very informative and practical session. You solve every doubts of eco views in day-to-day practice. Thank you, sir. Now I will welcome Dr. Tushar Parikh, sir. He did his DM neonatology from Safe GS Medical College, Mumbai, and also did fellowship in neonatology from Australia. Currently, he is a head of neonatal department at Motherhood Hospital, Pune. Over to you, sir.
Thank you so much, Dr. Vilas. My slides are visible. Am I audible?
Yes, sir. Audible and visible also.
Great. First of all, a very good evening to all of you. Let me thank the organizers of West Zone NeoCon, Dr. Mohit Sani, Dr. Kiran, Dr. Vilas, and all the organizers who have invited me for this workshop. Unfortunately, I will not be able to come for the physical hands-on part, but I'm happy that at least I'm able to contribute on online session. It's I think 9:43 or something, so I'll try and finish it in half an hour time. Yes, let's start. So pulmonary hypertension is a nightmare that all the neonatologists face every now and then. And when we talk about pulmonary hypertension, basically, I will start with beyond neonatal period. So if you look at, a child after 1 month, the pulmonary arterial pressure is age independent. So it is generally about 14 plus minus 3 millimeters of mercury. And pulmonary hypertension is diagnosed if mean arterial pulmonary pressure is above or equal to 25 millimeters of mercury. Now, what happens in neonatal period? In the neonatal period, because the baby in the fetus, the lung is partially collapsed, there is high amount of resistance for the blood to go through the pulmonary circulation. Only about 15% of the cardiac output goes through the pulmonary circulation. And as soon as the baby is born, the lungs open up, the mechanical resistance part to the circulation of the blood through the lungs reduces. And because of that, gradually the pulmonary pressure is reduced. Now, the entity of pulmonary hypertension, we call it when this pulmonary pressure does not reduce. Now, how to diagnose it? The gold standard is cardiac catheterization. But if there is no catheterization available, especially in the newborn, it is very difficult. So in that case, the criteria to diagnose pulmonary hypertension will be when the mean pulmonary peak pulmonary artery pressure is greater than or equal to 25 millimeters of mercury, or pulmonary vascular resistance greater than 3 Wood unit per meter square, or pulmonary capillary wedge pressure is less than or equal to 15 millimeters of mercury. So all these things are difficult in the newborn, and therefore we rely heavily on the echocardiography to diagnose pulmonary arterial pressure. So the role of echo in pulmonary hypertension is number one, to diagnose pulmonary hypertension, presence of it. Number 2, to exclude congenital heart disease. Number 3, to quantify pulmonary pressure. Number 4, to assess biventricular function. Now, this is very important because when the heart is facing pulmonary hypertension, many a times there is biventricular dysfunction, and that we need to assess because that will help you to monitor the therapy, and the echo will help you to monitor response to pulmonary vasodilator therapy. I would like to keep the talk simple from the point of view of basic workshop, and all of the participants should at least be knowing these 3 important parameters to diagnose pulmonary hypertension in the newborn. Now, the first one is peak velocity of tricuspid regurgitation jet. Second one is assessment of PDA shunt, and third one is acceleration time in main pulmonary artery. Now, these are the 3 important points which are going to talk. Besides that, there are many more indices. We look for size of RA-RV, assessment of the interatrial shunt, geometry of the interventricular septum, left ventricular eccentricity index, pulmonary regurgitation, and paradoxical septal movement. So I will talk about this a little bit later on, but first we will focus on first 3 parameters. As a basic workshop trainee, I would expect that you are knowing about these 3 important parameters to assess pulmonary pressure. The first one is tricuspid regurgitation jet. I'm sure all of you would have seen, or this is something which is commonly done. So when the pulmonary hypertension is there, it leads to dilatation of the RA and RV, and in the process, tricuspid valve ring also gets dilated. And with each systole, a jet of blood leaks from RV into RA. Now the velocity of this TR jet is measured, and application of modified Bernoulli equation, that is pressure gradient between the 2 chambers, is equal to 4 into velocity square, is used to derive the systolic pressure gradient between the RV and RA. If this looks too complicated, don't worry, I am showing it here. So what you do is that you go to apical 4-chamber view. The orientation marker will be facing around 2 or 3 o'clock position, and the probe is placed just below the nipple on the left side with the direction towards the right shoulder, and the orientation marker towards 3 o'clock, 2 or 3 o'clock. So this is standard view for apical 4-chamber view. And what you get is a picture like this, where the heart is resting on your probe, and the LV, RV, LA, RA, you will see, identify the structures, identify the walls. And then when you put a color Doppler, put it on the right side at tricuspid wall, you will see a regurgitation of the blood from RV into RA. Now, a lot of people do it inverse, so that the image will be seen reverse, that you're looking from down, but most of the neonatologists are comfortable doing it this way. So I have put it the image in a same format that we do the entire examination of the heart. Now the color Doppler is superimposed, and the regurgitation jet is basically tricuspid regurgitation. Now continuous wave Doppler is used as the velocity is likely to be more than 2 meters per second. And if you use pulse wave Doppler here, you will get a phenomenon which is aliasing. And so because of that, you will get the exact velocity of the blood across the tricuspid wall if you do the continuous wave Doppler at this point in the velocity. So the Doppler gate is aligned to the flow, and the flow away from transducer is seen below the line. So what you get is a flow like this. The Doppler signal envelope must be complete. So this is very important. You may have to do some alignment, rotation, tilting, maneuver of the probe so that you get a complete envelope. So what is complete envelope? So the regurgitation jet should be completely seen. And when you do that, make sure that you take the highest measured velocity as the pulmonary pressure, because this is the peak velocity across the tricuspid wall that we want to measure. So as it is shown here in the picture, you place the probe at the tricuspid wall, and the velocity of jet across the tricuspid wall you're measuring, and that velocity here in the picture has come 3.85 meter per second. So the pressure gradient is calculated using the modified Bernoulli equation, which is pressure difference is equal to 4 into TR velocity square. And so here what you do is that first you put the 2D echo, try and get the image. this is little subcostal. It is not exactly apical, but it's acceptable. You do a probe, you do a color Doppler, look for the regurgitant jet, and put the continuous wave Doppler at the regurgitant jet, and you will get a velocity waveform like this. Measure the highest velocity, and you must have a complete envelope. Now, if you see here, I was referring to this particular. Maybe I'll have to use a pointer. So if you look at these envelope, these are not complete, so you can't interpret, but the envelope has to be complete like this, and take the peak velocity there. Now here the peak velocity is coming somewhere around maybe 3 few meter per second, and the pressure gradient between the two chambers has come 56. Okay. So what happens is that so the pressure gradient between the two chambers you calculated, you add right atrial pressure, because you want to assess what is the pulmonary arterial pressure, and the pulmonary arterial pressure is equal to right ventricular peak systolic pressure, and the right ventricular peak systolic pressure is nothing but the pressure gradient plus right atrial pressure, because you measured the pressure gradient, and that right atrial pressure by convention is taken as 5 millimeters of mercury, and therefore the right ventricular peak systolic pressure, say if you take the previous example, the pressure gradient between these across the tricuspid valve you got is 56 millimeters of mercury. So the right atrial pressure will be, or right ventricular peak systolic pressure will be 56 plus 5 of right atrial pressure, and that will be 61 millimeters of mercury. Okay, so the right ventricular peak systolic pressure is 61. Now, how to diagnose pulmonary hypertension? So if you are getting right ventricular, so there are various different definitions, and these definitions are very important when we talk about pulmonary hypertension in a preterm baby, because the same blood pressure does not exist in preterm babies. In preterm babies, the systemic blood pressure is low, as well as pulmonary pressures are also low, and we have to compare the pulmonary arterial pressure with the systemic blood pressure. So the right ventricular systolic pressure upon systolic blood pressure, okay, if the ratio is above 1:2, then consider it as pulmonary hypertension. So there are definitions, so I'll go forward here. So how do you decide severity of pulmonary hypertension? So it is a basically gradient based on the ratio of right ventricular peak systolic pressure divided by systemic blood pressure. So if the ratio is, say, right ventricular systolic pressure is 40 and your systemic blood pressure is 40, the ratio is more than 1. So this is the suprasystemic blood pressure. Moderate when it is above 50%, and none or mild when it is less than 50% of the systolic blood pressure. Okay, this is clear. So you compare the pulmonary artery pressure with the systolic blood pressure, or the simple criteria will be, definition wise, if you have in a full-term baby, if the right ventricular peak systolic pressure is less than 40, it is mild. If it is 40 to 60, it is moderate, and it is more than 60, then it is definitely a severe pulmonary arterial hypertension. So for full-term babies, because most of these babies are asphyxiated or meconium babies, and therefore this helps very well, that when you have a right ventricular peak systolic pressure around 30-40, it is mild, 40 to 60, it is moderate, and more than 60 is severe. But when you talk about a preterm baby, go with this upper classification, where you compare it with the systemic blood pressure. So again, I am showing the same figure here. So the pressure difference is 4 multiplied by velocity square, and here the velocity is 3.74 meter per second, and therefore the pressure gradient across the tricuspid wall is 56, and therefore the right ventricular systolic pressure is 61. So this is a severe pulmonary arterial hypertension. Okay, now there is another way where you can see the tricuspid wall, and that is parasternal long axis view. So for that, So rotate the probe so that the orientation marker is towards the right shoulder. That is around 10 o'clock or 11 o'clock. And try and get the parasternal long axis view. Now, commonly the view we get, this is the midline view, and tilt the probe little bit medially, and so that you will get this particular view, which is basically a tricuspid valve view. So you try and get this tricuspid valve view. This is the right atrium, this is the tricuspid valve, and this is the right ventricle. And you try and interrogate it here and try and get a regurgitant jet of tricuspid regurgitation. So this is the picture, and this is the anterograde flow, but there will be regurgitation flow there. And when you put a probe there, you will get a regurgitant velocity like that. Again, the same modified Bernoulli equation, 4 into velocity square will give you the pressure gradient, and right atrial pressure is generally taken as 5, and therefore you will get the pressure gradient. So hence the pulmonary arterial systolic pressure is this much. Okay, so this is how you calculate the pulmonary artery systolic pressure. Is it clear? Is there any doubt over here? So this is the by method which you will do the commonest. You will use this method. Okay, so let's move on to the other two methods. One is by ductal shunting. So the blood flow across PDA depends upon the relative pressure difference between the aorta and pulmonary artery, understandably so. And by measuring the velocity of jet, the systolic pressure gradient between the pulmonary artery and the descending aorta can be measured using modified Bernoulli equation. And pulmonary arterial pressure can be derived by adding or subtracting the pressure gradient from the aortic pressure. So what you do is that you try and get a ductal view. As you can see, this is a dilated duct, rather I should say large duct, which is non-constricted, and you will try and get the color Doppler there, and then you put the pulse wave Doppler, and if the velocities are high, you can use a continuous wave Doppler at the PDA level, and you will get the direction of the shunt across the PDA and the velocity. So here, as you can see, this is the left to right shunt because it is above the baseline, and the velocity is around approximately 1.29 meter per second. It is measured. So this peak velocity of left to right shunt, and therefore the pressure gradient across the PDA is 5.8 millimeters of mercury. Now, because it is left to right shunt, I have to subtract it from the aortic systolic pressure. So aortic systolic pressure was 40, or systolic pressure was 40, and therefore the pulmonary artery pressure was 34.2 millimeters of mercury. So this is how you calculate across the PDA. Now what happens if the shunt is purely right to left? So here there is a mistake. It's not left to right, it is right to left. So because you are seeing the flow across the negative flow across the PDA. So here, as you can see, the pressure gradient is the flow is 2.7 meter per second, and the pressure gradient is 29.3. And if the systolic pressure is 40, then pulmonary systolic pressure is 40 plus 29.3. So which is 69 millimeters of mercury. So in this case, the pressure is very high. So the baby is having severe pulmonary hypertension. So what happens if the shunt across the PDA is bidirectional? So we have to remember that the pressure wave from the right side arrives before that from the left side at the level of the PDA. And the duration of the right to left shunt, if it is more than 30% of the cardiac cycle, it is considered significant pulmonary hypertension, and this is validated using the cardiac catheterization. So if the duration of right to left shunt is less than 30%, measure the left to right peak velocity. And if the duration of right to left shunt is more than 30%, measure the right. So I'll show it here. As you can see it here, there is a left to right. This is a bidirectional shunt. But if you see the right to left component is less than 30% of the cardiac cycle. So this cardiac cycle starts from here and it ends here. So if you measure this timing, it is visually, as you can see, it is less than 30% of the cardiac cycle. And therefore this consider, so when you measure the peak velocity, so you measure the peak velocity and you minus it from the systemic systolic blood pressure. So here in this case, we have done the measurement and this is 18%. So the right to left shunt component is only 18% of the cardiac cycle, and therefore the pulmonary pressure is subsystemic. Similarly, this is another picture where, as you can see, the right to left component, which is below the baseline, and left to right is above the baseline. So in the entire duration is 170, it's 450. So this duration from start from this point to this point, or cardiac cycle, is 453 milliseconds. And the right to left component is 176, which is about 38%. Hence, the patient has suprasystemic pulmonary arterial pressure. So this is very important. Even if the flow is showing bidirectional, the right to left component is more than 30% of the cardiac cycle, and therefore we consider this as a suprasystemic blood pressure. So this is the second method, but here we have to remember for the PDA, there are 2-3 important caveats. PDA is not always open. So when the PDA is not there, you cannot measure the pulmonary arterial pressure based on this particular method. Number 2, if the PDA is constricted, that will give some resistance to flow across the PDA, and therefore this method is not validated when the PDA is constricted. So this is only useful when the PDA is unconstricted and open PDA, then only this will give you some idea about pressure difference between the two sides, right and left side. Now coming to the next is acceleration time in main pulmonary artery. So as pulmonary artery pressure rises, the time to peak velocity or acceleration time gets shorter, and this acceleration time is confounded by the heart rate. And to avoid that, a ratio of time to peak velocity to right ventricular ejection time is taken. So normal ratio is more than 3, and a ratio less than 2 is considered as pulmonary hypertension. So what you do is that high parasternal short axis view, where you put the probe in the high parasternal area with the orientation marker towards 3 o'clock. And this will open the moustache sign, or the main pulmonary artery will be able to see. Put the pulse wave Doppler there, and you will get beautiful flows like this. Okay. Now, so what you do? So this is the start. This is the time to peak. So if the time to peak velocity is here, it is more than 3 seconds. So it's a normal. So RVET, you measure the timing. So here RVET is 164 milliseconds. Time to peak velocity is 57, and therefore the ratio is 0.34. So this is a normal TPV upon RVET. Instead, here, as you can see, there is a sharp pointed triangle, and TPV upon RVET is 0.17, which is suggestive of high pulmonary arterial pressure. So as you can see, this particular patient, the pulmonary artery waveform was like this, and the TPV upon RVT was less than 0.2. Also, so by these 3 methods, there are pluses and minuses, but as I can tell you with experience that tricuspid regurgitation jet is something which is done universally, and it is kind of repeatable, accurate, direct relationship. So we use it very well. The only problem with tricuspid regurgitation is that if the heart is failing and the pulmonary, the right ventricle is not pumping well, you may not get a good tricuspid regurgitation jet, and that may underestimate the pulmonary arterial pressure. Ductal velocity we saw, if the duct is constricted, then there is a problem, and TPV upon RVT has got a poor repeatability, and there is inverse relationship with systolic pulmonary arterial pressure. So again, there are pluses and minuses of each. So tricuspid regurgitation is something which is very doable. Now, when I say this, all these indices, let me ask you a question. How do you define obesity? Little diverging. How do you define obesity? So if you go through the WHO definition, these are the definition: body mass index more than 30, absolute waist circumference more than 102 in male and 88 in women, and waist to hip ratio more than 0.9 for men and 0.85 for women. How many of you remember or know this definition? Do you want to know how much is the abdominal circumference here to define, or what is the body mass index in this person to call him obese? Absolutely no, because you all can see there is overhanging belly, there is acanthosis nigricans, there is gynecomastia, there is excess fat in the nuchal area, and so basically this person is obese. Now you tell me a ratio telling me that this person's abdominal circumference is 100 centimeters. It is less by 2 centimeters. Therefore, he is not obese. So it's not correct, isn't it? So basically, it is not only about the indices that you get. It is what you see and that will tell you whether it is a pulmonary hypertension. So now can anybody tell me out of this left or right heart is likely to have pulmonary hypertension? You can write in the chat box. Yeah, so there are some answers. Right, so it is the right side is the one which is likely to have a pulmonary hypertension, because in the right picture there is a dilatation of RA and RV as against the left side. Now, if you go to the next one, you put the color Doppler and you will see the regurgitation. Now, going to the interventricular septum assessment, so you do it in the parasternal short axis view, and where the orientation marker is facing towards 2 o'clock. Okay, and then Dr. Mohit beautifully showed this, and here you will be able to see the interventricular septum. Now, when you do it in this image 2 and image 3, as you can see, this is the interventricular septum part. Okay, or here this is the interventricular septum, and this part, the lower part, is a free wall of the left ventricle. Okay, and the right ventricle is on top here, crescentic on top here. Okay, so this is how it is normally seen, that interventricular septum works or pumps the heart as if it is a part of the LV, and it moves along with LV, and it forms a circular chamber like this. But what happens if you have a chamber like this, where the interventricular septum is become flat and the LV cavity is become nothing like it, it's become a D-shaped LV. So this is another sign that the child has got severe pulmonary hypertension, that the interventricular septum is pushed towards the left side. Also, there is something called as LV end systolic eccentricity index. Okay, so I will not talk, but basically what you do is that end systole, when the heart is at the smallest dimension. So this is the line which is parallel to the interventricular septum, S1, and this is the line which is a perpendicular to S1. This is S2 line, and you take the ratio of S1 upon S2, and if that ratio is more than 1.2, it suggests pulmonary hypertension. And this is again in the newborn. But please remember that if you don't get a ratio exactly like this, don't get, because all the signs are very important. Now there is something, again we go for a high parasternal pulmonary artery view. Now what happens with pulmonary artery view, if you are seeing the pulmonary regurgitation, now that is another indication that the pulmonary arterial pressure may be high. And in that case, you can do a gradient across the pulmonary wall and see the pressure difference between the pulmonary artery and the RV chambers. Then when we do a main pulmonary artery Doppler for TPV upon RVAT, again look at the waveform shape. If the shape of the waveform is a sharp pointed triangle like this, it indicates that there is a severe pulmonary arterial hypertension. Also, you can assess the intra-arterial shunt, and the same principle applies. You do intra-arterial shunt assessment, put the Doppler there, and the waveform across the intra-arterial septum will be something like this. Initially, there is a negative deflection because, as I said, the electric impulse in the heart comes on the right side first and then on the left side. So the right-sided chambers, they contract slightly earlier than the left side, and therefore you will get some negative deflection initial part, and then the entire will be positive deflection. Again, with the same principle, if the negative deflection is ratio is more than 0.4, it is abnormal, and less than 0.3 is normal, and 0 to 3 to 0.4 is borderline. So if you see the ratio of right to left more than 40% of the cardiac cycle, then it is definitely abnormally high pulmonary arterial hypertension. Or if you are seeing, so this is the example of PPHN, where you will have right to left component more than is 0.47. Or this is a scenario where there is purely right to left pattern at the interarterial septum level. This is absolutely not normal, not even in pulmonary hypertension, and this can happen in situation of TA-PVC. So if you are seeing pure right to left shunt at interarterial septum, then it is TA-PVC unless proven otherwise. Again, along with this, there is a right ventricular dysfunction commonly. So you can assess the right ventricular dysfunction by these methods, and by eyeballing and by right ventricular fractional area change and TAPSE. We will not talk in detail, but what you do is that you go to apical 4-chamber view, get the right ventricle, get a good view of the right ventricle, freeze the image, go backward, roll the ball backward, and try and get the maximum dimension of the right ventricle. make the area calculation by the machine, then roll it so that you get the narrowest area of the right ventricle. To calculate the area with the help of machine, and that will give you the area value. So as you can see here, the maximum area is 6.7 meter per square, and here it is 5.4. And when you do the fractional area change, the fractional area change is about 25 to 26% at birth, and in full-term babies and adults, it should be above 35%. So in a preterm baby, 26% is okay, and in full-term baby onwards, it should be above 35%. Similarly, there is something called as TAPSE. That is, these are the right ventricular function assessment measures. The first one is a right ventricular fractional area change, and the second one is TAPSE. So the TAPSE is tricuspid annular plane systolic excursion. So what you do, go to apical four-chamber view, M-mode cursor through the lateral portion of tricuspid valve, and excursion of tricuspid valve from the base of the heart towards the apex. Okay, so what you do is that apical four-chamber view, identify the hinge point where the tricuspid valve is attached to the annulus, and put your M-mode beam through the lateral angle of the tricuspid valve through the annulus of the tricuspid valve, and what you get is this. Okay, and you get a velocity like this. This movement is basically tricuspid annular movement towards the apex, and this movement can be measured. It is in preterm babies, it should be above 4. In term babies, it should be above 8, and in adults, it should be above 15 millimeters of mercury. So if it is less, then the right ventricle is not functioning well, and you may need to add something to improve the right ventricular contractility. So summarizing my talk, PPHN is diagnosed by echo by assessment of TRZ, PDA shunt, and TPV upon RVAT, that is time to peak velocity upon the right ventricular ejection time. These are the 3 important parameters. Plus visual assessment of PPHN is done by evaluating chamber size, anatomy of interventricular septum, shape of pulmonary artery ejection waveform, whether it is tongue shaped or whether it is a sharp pointed triangle, and PFO shunt assessment, what is the type of shunt, whether it is a left to right or right to left. And right side cardiac function is very important because the RV dysfunction is very, very common in PPHN. Thank you very much. Are there any questions?
There are questions.
Yeah.
There are questions. Vilas. Then the questions are, can we measure the jet gradient in the subcostal view?
No. So the subcostal view, as I said, subcostal view is not meant for aligning with your tricuspid jet. Sometimes if you are not able to get a good apical four-chamber view, if you come little medially, you may get a good view of the tricuspid valve, but then you may not be able to get the good velocity and complete velocity, because there will be some angle of insonation, and that will underread your velocity, and therefore the gradient you will be able to measure will be less. So it should be done in apical four-chamber view or parasternal long axis view in the first image. Yeah, in the medial image.
Thank you, sir. So these were the questions, and I would like to thank Dr. Tushar very much for very precisely explaining regarding the indices in the PPHN. Thank you very much, sir. So in the next session, that was supposedly was Dr. Kiran More's session, was regarding the shock, but because he is there in the central zone neocon and he's traveling, so that's why there is a change in the schedule. So instead of him, we will be taking the normal views and pathologies in the lung ultrasound. For that, we are really thankful to Dr. Sujit, who has agreed instead of 24th for today's session. So we have Dr. Sujit. Dr. Vilas, can you introduce, please?
Yes, sir.
You are mute. Vilas mute hai. विलास तो म्यूट हुई है.
Yes, sir.
हाँ. So Dr. Surjit is
Good
there,
evening.
so you can introduce her.
Yes, sir. Good evening, ma'am.
Yeah, good evening.
Hello.
Good evening. I'm here.
Yes, ma'am. Welcome, ma'am, in this eco workshop. Next session is on basics of shock indices. Ma'am is
No.
consulting
It is
neuromorphic.
not. It is not the shock indices, Vilas. There is a change of change of program because Dr. Kiran's flight got late, so he couldn't reach. So that session is we postponed it to 24th. So instead of
Okay,
that
sir.
shock indices by Dr. Kiran, we will have the lung ultrasound, normal lung ultrasound views and pathologies by Dr. Surjit Madan. She is the
Okay.
practicing neonatologist in Jalandhar, and she's being very active in the POCUS groups and in the POCUS teaching. So we are really fortunate to have her for our lung ultrasound, normal views and pathologies. So over to you, Dr. Sujit.
Yeah, good evening, everyone. Sure.
Dr. Sujit, first open your presentation and then share your screen.
Okay.
You can unshare, open up your presentation and then share your screen. So I would advise everyone to go through the manual for the workshop that we have that I have shared in the group, and that will be helpful for your hands-on stations. Yes, we can see your screen, Dr. Sujit, so you can maximize it. Yes, thank you.
Hi, good evening, everyone. This is a different lecture in between all the eco lectures. So first of all, I would like to thank the organizers of Guj Neocon for inviting me in this focus workshop. So I think it would be definitely a change from the eco topic. So like today's topic is basics of lung ultrasound, and we'll cover a few of common pathological lung conditions. Hope the screen is visible now. Yeah, so we'll start with a few basic principles and how to do lung ultrasound in neonates. So as we all agree, when we do a bedside physical examination during our bedside rounds, we do inspection, palpation, percussion, and auscultation. And now insonation has become the fifth pillar. So we'll just go through basic principles, how we do ultrasound in neonates. Like we have different medias when we plan to do a scan. Like there are air, we encounter bone, fluid, and soft tissues. And air is known to be a bad conductor of ultrasonic waves, and it reflects all the waves like a mirror. And bone is known to be an enemy of ultrasound waves, and bone absorbs the sounds waves, but it doesn't let it pass. And the fluid is a lover of ultrasound, and the fluid lets ultrasound beams pass very easily. So, and soft tissue is like ultrasound wave is very friendly with the soft tissues. More the soft tissues are present, more easily the waves can pass. So what in a standard ultrasound examination, what we do in general, that the ultrasound beams penetrate the tissue or fluid, whatever it encounters, and it is reflected back to the transducer from the interposing structures. So then the machine interprets the strength of these returning signals and it creates an image on the screen. So then our interpretation of this scan is actually a reconstruction of what the ultrasound beams actually penetrate. But it is a little different in lung ultrasound. What actually happens is the ultrasound beams, as I told, cannot penetrate the air, and it gets reflects back and it creates a few artifacts. The machine then displays a picture of these artifacts. And our interpretation of the scan is not a reconstruction of what the ultrasound beam penetrates, but of a pattern of artifacts. I'll explain a little more that what is artifact. An artifact is actually something which is visible, but it doesn't actually represents the anatomical tissue of what it is scanning. It's more like a mirage. What does it mean for us is that, especially in lung ultrasound, we have generated patterns with the artifacts to kind of recognize normal or abnormal patterns. And we relate this to the various pathological states, which are actually related to air and water content of the lungs. So when in a lung ultrasound, we are actually not exactly interpreting the tissue, but actually there are some lines which are called as artifacts. They might be horizontal lines or vertical lines, so which keep on varying in normal and abnormal lung. So in certain situations, like when there is more of fluid, or the fluid is excess, or in lung tissue there is some abnormality, or the lung tissue is damaged, then we interpret these artifacts differently. And then we correlate these artifacts with certain pathological conditions of the lung. So why can't we do a chest X-ray? Why is lung ultrasound needed? There are some drawbacks of this chest X-ray and CT scans, that it is a time-consuming process. And it needs transportation. And previously, what we thought, there was nothing better available. So let us continue with chest X-ray and CT scan. So, and the sensitivity and specificity of X-ray is less. And as we know that we are exposing our babies to multiple X-rays and radiation several times. So lung ultrasound is, we'll see where we can use lung ultrasound. When a baby comes to you in your NICU with respiratory distress, or you have a baby in NICU and there is suddenly deteriorating, there is deterioration in the respiratory status, or your baby is having cyanosis, retractions, grunting, apnea, or antenatally you have diagnosed some lung abnormalities, or you want to see, you have given antibiotics or even chest physiotherapy, or diuretics, or surfactant, whatever, and you want to see the response to your treatment. So you can repeatedly do your lung ultrasound multiple times to see how is the response to your treatment. And before giving surfactant in preterm babies, you can do your lung scoring, and post surfactant you can do lung scoring. And this will guide you whether your baby needs a surfactant a second time or third time. And then you will monitor how is the progress of your baby's respiratory illness. So you can do lung ultrasound in different pathological conditions, like to diagnose RDS, in TTNBs, in pneumonias, in pneumothorax, in pleural effusions, in pulmonary edemas, in CLDs, and monitoring the response. And you can even do before weaning from the respiratory support, or during thoracocentosis, you can use this procedure. So why do we do lung ultrasound? What are the advantages of lung ultrasound? It's a dynamic technique, and it allows for analysis of lung movement in real time. At that time when you're scanning, you can see what changes are happening in the lung. So it is very quick process. It hardly takes 2 to 3 minutes. And you know that chest X-ray takes long time. And it's a bedside test. There is no radiation. So you can do lung ultrasound multiple times for your babies as and when needed. And neonates have thinner thoracic wall, small width of thorax, easy to do lung ultrasound. Sensitivity, specificity in different conditions is much higher than chest X-ray. And it guides us for the thoracocentesis, for fluid management, for lung recruitment. And the good thing is that you clinician, as a clinician, you yourself are performing and you're interpreting and correlating it with your course of the baby in the hospital, the clinical condition, the screening, the blood investigations. You can correlate with the clinical signs and symptoms of the baby and then interpret and then decide what treatment is needed. So only limitation is that it is operator dependent. You have to learn. That is what we are doing today. We are trying to learn it, and this will help us to interpret and decide treatment for many babies, and it will help us in our NICU practice. So you must have gone through different kind of probes available for ultrasound. Here in lung ultrasound, we use a linear probe, which is high frequency because we are doing it for the neonates. So frequency of more than 9 megahertz is used. So this is a linear probe, right? We also have hockey stick probes, which are used for preterms, extremely low birth weight babies. Why? Because they have high frequency probes and they have better resolutions. While doing lung ultrasound, your baby should be quiet. While doing any scan, echos, the cranial ultrasound, your baby has to be in a quiet state. You can soothe your baby, and better to do in a supine condition. But yes, if your baby is in prone condition, you can do in prone also, and even you can do in side position, lateral position. But whenever you change the position, at least you have to wait for 30 minutes before you do your scan. So there are two methods to do a lung ultrasound. There is a 12 region technique and there is a 6 region technique. See, this is a 12 region method. When you do a comprehensive lung ultrasound, when you don't want to miss anything, you do a 12 region techniques. So your baby's chest anteriorly, lateral and posteriorly altogether is divided into 12 areas. So just look at these figures. This is the anterior, this is lateral, and this is posterior region. So anterior region is divided into 4 areas. Right, left, again upper and lower, upper and lower. Lateral is divided into 2 regions, upper and lower. And posteriorly again is divided into 4 regions, right and left, upper and lower. So this is the anterior chest. So you have a right, upper and lower. So the right upper area means the upper border will be your clavicle. Medial border of your region will be the medial sternal edge. The lower will be the mammary line and the lateral will be the anterior axillary line. And again, the lower area on either of the side, the upper line of this will be the mammary line. The medial will be the medial sternal edge. The lateral will be the anterior axillary line and the lower will be the abdominal organs. In similar way, it is same on the left and on the right side. So anterior area we have divided into 4 regions. So you have to keep probe in the right side upper and lower, in the left upper and lower separately to see different regions. This is a lateral area. Again, lateral area is divided anterior into anterior axillary line and posterior we have posterior axillary line. And again, it is divided at the mid into upper and lower. So such 2 areas on the right side and 2 areas on the left side. And this is the posterior region. So posteriorly, again, right and left and upper and lower. So right upper area will be, the medial line will be your medial thoracic spine. And upper is just the neck and the lateral is a medial border of the scapula. And lower is the inferior angle of the scapula. This is a right upper area, posterior. And lower area, again, medial and upper are the mammary, this line, and the medial spinal. And this is a posterior axillary line. And lower is the abdominal organs. So in this way, you are dividing your baby's chest into 12 regions. So for a comprehensive lung ultrasound, you will do scan in all the 12 regions so that you don't miss anything. So another technique is 6 region techniques. So 6 region techniques is just for a quick assessment of lung ultrasound. So in routine, you can do just a 6 region also. So in this, what happened? One is the anterior area, another is lateral, another is posterior. on the right side and left side. So left side you have 3 regions, right side you have 3 regions. So you are not dividing the regions into upper and lower area. It is just one anterior, one lateral, and one posterior. You will keep your probe into 3 regions on the left side and 3 regions on the right side. So 6 region technique is also good enough. So you do a 2D or grayscale in lung ultrasound, which is commonly done, and M mode is also done for the Mowing interfaces. So how do we keep the probe? This is how we keep the probe. This is a linear probe. I have kept it perpendicular to the chest wall, no tilting, no twisting. And this is a probe marker, which is towards the cranial end, towards the face of the baby. And you keep a 3 to 5 centimeters of depth. There's a depth option in your machine, and you have to adjust that depth when you do a lung ultrasound. So keep it around 3 to 5 centimeters. So this is an anatomical drawing of the superficial chest wall structures. So see, this is a skin. What do we get first? We get skin. Then we get subcutaneous tissue. Then this is a pectoralis muscle. These are ribs. In between the rib is a intercostal space. And this dark area which we are seeing is a pleural line. And the lower area is a lung parenchyma. When we compare it with a 2D view, so this is skin, subcutaneous tissue, pectoralis muscle, this anechoic area. This black thing is anechoic. The ribs are anechoic. So these are ribs. And below that is a parenchyma. We'll see in our further slides in detail. So when you start a lung ultrasound, the first thing which you see is a bat wing sign. How does it look? See, this is a bat, this is a body, and these are the wings, 2 wings. So this is a pleural line. This is a white echogenic line. And these 2 ribs on the left and right side looks like the wing of a bat. So this is called a bat wing sign. So whenever you start interpreting a lung ultrasound, just see whether you have the bat wing sign or no. This should be the first thing you have to see and mention. Second thing which we see is a acoustic shadow. We'll go one by one how a normal lung ultrasound looks. Just concentrate on this black area. This anechoic area, black round things are ribs. This is an intercostal space. So this black area below the bone is called as acoustic shadow. You have to even see this while doing scan. What is acoustic shadow? I'll tell you. When the ultrasonic waves travel, they first hit the skin, subcutaneous tissue, muscles, ribs, pleura. And these ultrasonic waves will reflect back from ribs and pleura. And you will give some interpretation, some artifacts, which I mentioned before. So some ultrasonic waves will scatter off. Many will reflect back from the rib because I told bone is a bad conductor of ultrasonic waves. But it means that it is a good reflector. It reflects back all the ultrasonic waves. And these waves cannot penetrate. Because the waves are not able to penetrate, you can see this dark area below the ribs. What we call it as acoustic shadow of ribs. This is how a normal lung ultrasound looks. These are ribs. This is a pleural line. So this looks like a bat wing sign. So a bat wing sign is present. We can see 1 rib, 2 rib. This is 3rd rib, another here rib. And this is an acoustic shadow. I just mentioned this black area. We have acoustic shadow over here. This is an intercostal space. We'll show you what all these things are. So we have learned bat wing sign. We have seen acoustic shadow. Then the 3rd point is pleural line, which you have to see while doing the scan. See this white line, echogenic line. It is thin, smooth, regular, uninterrupted, hyperechogenic. Hyperechogenic means white. It's white, looking white line is called as pleural line. It is less and its thickness is less than 0.5 mm. And it is 0.5 centimeter below the pleural line, rib line. This line always indicates the parietal pleura. It is always a parietal pleura. and it is formed by the eco-reflection of the pleural lung surface interface. So when this pleural line moves to and fro as synchronizing with the respiration, that is called as lung sliding. We come in detail. What is lung sliding? There are two pleuras, right? Visceral pleura and parietal pleura. And these are two. And they are in between, there is minute amount of fluid. So when the baby is during the respiration, this moves like this, slide over each other with the respiration. This sliding movement is called as lung sliding. It is a dynamic phenomena and it appears like a shimmery. It appears like a shimmery ant march appearance, and it is indicative of a healthy lung. I'll show you a video how it looks. So the pleural surface, whenever you are seeing a lung sliding and good A lines, I'll tell you what A lines are, then it indicates that maybe there is absence of lung pathology in your area. So see this video. This is pleural line. Can you appreciate that there is some shimmery ant-like marching here? I agree it is very difficult initially to recognize, but as and when you keep doing more and more scans, you can appreciate this lung is sliding. This pleural line, in this pleural line, there is sliding. So this is a good sign. Lung sliding can be sometimes absent. In very common condition where it is absent is pneumothorax. Remember this one point. You can be absent in pleural effusions, massive pleural effusions, in pneumonia, severe ARDS, pleurodesis, when there is pneumonectomy. But most commonly we come across in pneumothorax. So next are A lines. A stands for A lines. A stands for air. A stands for awesome. Why did I write this? Because I'm very happy when I have good A lines. So I say, wow, this is an awesome lung ultrasound when I see good A lines with few other features also. So how are A lines seen? They are again reverberation artifacts. I'll tell you what reverberation means. These are again artifacts which are caused by the pleural line. How? I'll tell you. They are echogenic, horizontal, parallel lines, straight horizontal lines. They are equidistant from each other. A indicates air. It could be physiological or it could be pathological. And the distance between two A lines equals to the skin pleural line distance. I'll tell you how they are formed. See, these are A lines. I'll show you first this. This is a pleural line. This is one A line. This is second A line. This is third A line. This is fourth. So they are horizontal echogenic lines which are parallel to the pleural line. They are formed due to reverberation of the pleural lines. They're smooth linear lines. This looks like a bamboo stick, right? There are bamboos and you see lines in between. This actually looks like a bamboo stick. So they are hyperechoic parallel lines and they're equidistant from each other. So let's see how they are formed. See, what does, first of all, a reverberation means, I'll tell you. See, this is a transducer. These are the ultrasonic waves. So coming down and it will first hit the skin. It will hit the subcutaneous tissue. Whatever structure it hits, they come to a structure and the energy which is released interacts with the structure and that structure moves. This concept of structure moving is called as reverberation. In general, this is reverberation. So when these ultrasonic waves hit the pleura, this is pleura, this line. When these ultrasonic waves are coming, they hit the pleura. When they hit the pleura, what happens is that ultrasonic waves will penetrate in and then they will cause a pleural layer, reverberation. The pleural layer will move. When the energy hits the pleural line, pleural layer, it moves. There is reverberation of the pleural layer. And this produces the parallel lines. See, it hits here, this pleura moves. There is reverberation. So reverberation of this pleural line will cause these lines. These are horizontal echogenic lines, which are called as A lines. Right? So these are A lines I showed you. So this is a video. These are the ribs. This is a bat wing sign. This is a pleural line, which is, and I appreciate that there is good pleural sliding also. Lung sliding is good. There is shimmery movement. And this is A lines. 1 A line, 2 A line, and there's another third. So this is bamboo stick-like appearance. These are A lines. So to me, this looks like a good lung, good normal lung. So next, let's see what B lines are. B lines are bad. I'm not very happy when I see a lot of B lines in my lung ultrasound. What are B lines? They are vertical lines, vertical laser-like lines. They are again hyperechoic. Hyperechoic means white. Hyperechoic artifacts, they start from the pleura and they go all the way down to the bottom of the screen. And they move with the pleura. When there is lung sliding, the B lines move with the lung sliding. Means they move with the respiration. And B lines are produced because there are reverberation artifacts within the fluid bubbles which are present in the interlobar and interlobular spaces. I'll show you how these B lines are formed. Before that, let's see. These are B lines. This is a pleural line. This line is a vertical laser line which is starting from the pleural line. It goes till the bottom of the screen. And these erase the A lines. These B lines move with the respiration and they erase the A lines. And you can normally see them within 24 to 48 hours of life. Later on, it is known to be pathological. See, this is another picture which will show you how there is reverberation and how this B lines are formed. This is again a transducer. The ultrasonic waves are passing here, right? This is a pleura. It hits. This is an interstitium. So this, and normally it has to be aerated. Normally interstitium has to be aerated. But depending upon the fluid which is there, the ultrasound, when there is a lot of fluid now, what happens? The ultrasonic waves, they get trapped in the fluid which is present. And it causes vertical reverberation artifacts. Initially, what we had seen, pleural line caused horizontal reverberations. But here waves, they get stuck in the fluid. So rather than creating the horizontal A lines, they obscure the A lines and there are vertical artifacts which are formed because the ultrasonic waves make this area shake in a linear pattern. And this will cause vertical lines which are called as V lines. So what happens? It hits and there is fluid over here. This will cause the ultrasonic waves to get trapped and vertical lines are formed which are called as B lines. And if there is more fluid in the lungs, there will be more B lines. So there is an interstitial syndrome, interstitial lung syndrome, hai na? Lung disease. Because in the interstitium, there is more fluid, more waves are getting trapped, there is more vertical reverberations and more vertical B lines and severe B lines are that's why seen in interstitial lung syndrome. So you can see B lines when there is pulmonary edema, there is congestive heart failure, there is pneumonias in RDS, in TTNBs, sometimes in the initial few hours and in lung contusions. So B lines diagnose a loss of peripheral lung aeration due to interstitial disease involvement. I showed you how these B lines look. These are B lines. They start from the pleural line and go till the bottom. So you can see few vertical lines which are starting from the pleural line, but they're fading away. So these are the comet tails. So you should know how to differentiate comet tails from the B lines. So they can be, as I told you, more fluid in the interstitium, more B lines. More severe are the B lines. So there are terminologies for that. Could be a simple B line, there can be confluent B lines, there can be AIS pattern. So these are simple B lines. Simple B lines means if there are 2 to 3 well-spaced B lines in your lung zone. So it is called as simple B lines. If in one intercostal space, there are many B lines, there are intense B lines in one intercostal space like this. This is called as confluent B lines. If such kind of confluent B lines are present in more than 3 intercostal spaces, see 1, 2, 3, 4. 4 intercostal spaces are having confluent B lines, then it is called as AIS pattern, that is alveolar interstitial syndrome. So these are different severity of B lines. This AIS pattern. In AIS pattern, see there is dense, many confluent B lines, more than 3 intercostal spaces, but this acoustic shadow is still seen. So when acoustic shadow is seen, then it is AIS pattern. There is another terminology which is called as compact B lines. It is kind of AIS pattern, dense B lines, confluent B lines, but the acoustic shadow is also obliterated, disappears. This is a pattern of compact B lines where you can't even see the acoustic shadow. Then you can name it as compact B lines. And this is what I told you. This is how AIS pattern looks. See, these are B lines starting from the pleural line going till the bottom, and 3 intercostal spaces, 1, 2, and 3 intercostal spaces are full of confluent B lines. So this is AIS pattern. Acoustic shadow is still visible. So this is not compact pattern. It is an AIS pattern. And these lines are obliterating the A lines, erasing the A lines. I've told you how comet tails looks. They're similar to B lines, but they fade away. They do not reach the bottom of the screen. So this is comet tail. These are B lines. That's how you differentiate. Don't get confused comet tails for B lines. So next common terminology which you should know is a seashore sign or sandy beach sign. You go to your scan, do lung ultrasound, in the intercostal space, put a M mode. You have a M mode button, click that in the intercostal space, you will get this pattern. Okay, what is this? This is sand, this is beach, sandy beach appearance. This is this dark echogenic line is a demarcation between superficial tissues, that is skin, subcutaneous tissue, muscles. This is a pleural line. And reverberation of pleural line, the sliding of the pleural line, when there is good lung sliding, the area below that, the lung parenchyma, you get a kind of artifact below the pleural line, which is having an appearance of sand. So it is called as sandy appearance. So this is sandy and this is beach appearance. So when you have this sandy appearance, it means that your lung is sliding. So you have a lung sliding, good lung sliding. So this is seen in a normal lung. So automatically when this lung sliding is absent, this sandy appearance should disappear. We'll see in a further slides. So in RDS, let us just go through few pathological conditions in short. To complete all the pathologies, it will take long time. So try to just highlight the important points of few neonatal pathological conditions which we usually come across in our NICUs. First is a RDS. In RDS, what happens? There is lung consolidation. There are air bronchograms. I'll show you in the pictures. Coming to pleural line. Pleural line is abnormal, might be disrupted, and it is thickened, and A lines disappear. There might be AIS pattern. There might be diffuse white lung. And in 15 to 20% cases, you might have unilateral or bilateral pleural effusion. So coming to the pleural line abnormalities in RDS. Pleural line might be irregular, disrupted, thickened. Normally, I told the thickness should be less than 0.5 mm. In RDS, the thickness will be more than 0.5 mm. And there will be subpleural consolidation. And the identification of pleural abnormalities have 100% sensitivity, but specificity is 45% because pleural line abnormalities can be seen in many other pathological conditions also. So one is pleural line abnormalities, thickness of the pleural line, subpleural consolidation. What happens to the A lines? There are lack of A lines because there are lots of B lines in RDS. So A lines are erased depending upon the severity of RDS. So when there is pleural line abnormalities, lack of A lines with lung consolidation, the specificity of RDS will be almost 100%. So we do lung scoring. There's a BRAT scoring, which we do in 6 regions of our lung, and we score them. So we do in what we do, we keep our probe only in anterior and lateral areas, not in the posterior area. Commonly, which we do, the BRAT scoring. On right side, you will put probe in right upper, anterior upper, right, anterior lower, and lateral. Again, left side, anteriorly upper and lower, and lateral region. These are the 6 regions which will keep the probe. You will do the scoring. Minimum score is 0, then 1, 2, 3. The maximum score is 3. So if the maximum score is 3 in all the 6 regions, the scoring would be, total score will be 18. So it cannot be more than that. So you have to do scoring from 0 to 18. And depending on the scoring, we can plan for surfactant therapy. So this is a BRAT scoring. This is how, this is 0, 1, 2, 3. I'll explain you. So these are the 3 regions: right side, anterior, upper, lower, and lateral. Left side, anterior, upper, anterior, lower, and axillary or lateral area. It's a BRAT scoring for lung ultrasound. How do you score? This is 0, this is 1, this is 2, and this is 3. 0 means you have A profile. You have very good A lines, good pleural line, good A lines, then you score it as 0. Right? This is 1. 1 is B pattern. If you have 3 B lines, more than 3 well-spaced B lines in your one lung ultrasound scan, when you keep your probe in that area, if you have more than 3 well-spaced B lines, then your score is as 1. If you have AIS-like pattern, confluent B lines, then it is 2. Score is 2. And this, can you appreciate the small dots below the pleura? This is called subpleural consolidation. So if in score 2, there might be some subpleural consolidation, which will be not very severe. There might not be subpleural consolidation. If you have an AIS pattern with or without minimal subpleural consolidation, you will score it as 2. When you have AIS pattern or compact B lines or whiteout with extensive subpleural consolidation, then you score it as 3. So this is how in your 6 regions, you will score it as 0, 1, 2, 3. See, this is subpleural consolidation. This is an extensive subpleural consolidation. Pleural line is disrupted. There are B lines, AIS-like pattern. You have subpleural consolidation. If I get such kind of picture in my zone, in my any of the region, I will score that region as 3. So this is a pattern. 0 is A pattern. 1 is B pattern. Presence of more than 3 well-spaced B lines. 2 is a severe B pattern. Severe B pattern means crowded B lines, confluent B lines, with or without subpleural consolidation. And score 3 is for extended subpleural consolidation, extensive consolidation. So in lung ultrasound, you have consolidations. And as I explained you, could be minimal subpleural consolidation or extensive. There will be different degrees of consolidation. And air bronchograms. I'll show you. These are air bronchograms. These are white, speckled, snowflake-like spots. These are snowflake-like speckled spots. These are called as air bronchograms. White, speckled, snowflake-like regions. These are called as air bronchograms. These are also seen in RDS. So next, coming to pneumonias. Pneumonias can also have different severity of consolidations. There can be hepatization in the subpleural lung tissue. It could be of various size, shape, positions. In pneumonias, you might have air bronchograms, fluid bronchograms, and there might be a shred sign. The boundaries of the consolidated areas are shredded, is irregular, jagged. Then the pleural line is also abnormal. It can be disrupted, irregular, disappeared, or coarse appearance. And the lung sliding can also be absent in severe forms. See, this is a shred sign. This is very pathognomic of pneumonia. Shred means what? This is a air bronchograms. This is a consolidated areas. The margin is shredded. See, it is very irregular. Shredded, jagged means what? When a rat has bitten a paper, how will it bite? This irregular, it will not bite in a very regular, with a regular margin. It will be very jagged and irregular. That kind of margin will be there in pneumonias in shred sign. This also, and you have to also correlate with the sepsis screen, your blood cultures, your course of the baby, your biochemistry. You have to definitely compare this with your clinical and biochemistry and culture pictures. And this is how shred sign looks. See, this is very irregular. Irregular margins. This is very pathognomonic. It's also called as freckle sign. This is a video I kept for you. This is a pneumonia. These white speckled snowflake appearance are air bronchograms. Here, the pleural line also look little disrupted, even here, and the margins are shredded. And see, this is confluent B lines are also present. This is hepatization of lung. When this is a normal lung, you can see the A lines. There's good pleural line. There is pleural sliding. But this area, if you can appreciate, looks like a liver. This is not liver. This is a lung which is hepatized. Next, coming to pleural effusion. So, it's not very fast. Enter. Yeah. In pleural effusion, there is quite more advantage of lung ultrasound than chest X-ray. For a chest X-ray to catch a effusion, you need minimum of 150 ml of fluid. But lung ultrasound can even measure 5 ml of, can detect 5 ml of pleural effusion. So the sensitivity is very good with the lung ultrasound. This is how pleural effusion can be seen. And next, coming to transient tachypnea of newborn. So this is how the picture looks. We know the physiology, what happens in TTNB. It is called a wet lung. You have wet lung physiology. So the fluid which is present will settle down and the air goes up, right? So the lower area of the lung will be wet. Wet means what? B lines. More of fluid means more of B lines. And aerated means this good air means good of A lines. So this, see this, the lower lung is having more of B lines, confluent B lines. The upper area is having A lines. So this is called B profile. This is called A profile. So the transition, the point in between that is called double lung point. So double lung point is one of the pathognomic feature of TTNB. This is aerated lung. This is interstitial edema. So one more point which differentiates RDS from TTNB is that in TTNB, there will be no subpleural consolidation. If subpleural consolidation is there, you take it as RDS. So next is pneumothorax. In pneumothorax, remember 3 to 4 points. There is no lung sliding. Lung sliding is abolished. Second, there are many A lines. There is A pattern. More because of more air. There is absence of B lines, absence of comet tails, and there is presence of lung point. These are 4 to 5 points which you have to remember in pneumothorax. So what happens in pneumothorax? There is absent lung sliding. Why there is absence? See, this is a visceral pleura, this is parietal pleura. There is minimal amount of fluid and it is sliding over each other. So when there is air in between, so these will not slide. And in one area, there is no sliding. In another area, it is sliding. So the transition between the lung sliding, which is normal, and abnormal area where there is no lung sliding, the transitional point is called as lung point. Right? And this is seen in pneumothorax. And there is 100% specificity of this. Look at this. This is a lung ultrasound. You put a M mode here. When you keep a M mode, this is a sandy beach appearance, which we saw because the lung sliding was present. You had a sandy appearance here. But in pneumothorax, there is no sandy appearance. This area also looks like an barcode sign. So this is called stratosphere sign or barcode appearance. So look at this. This is a normal lung. When you put an M mode, this is superficial tissues, this is pleural line, and this is sandy appearance, sandy beach appearance. In pneumothorax, this is how you see. This is called stratospheric sign or barcode sign. This is a video. If you can appreciate, I can see pleural line, but there is no lung sliding. You cannot see that shimmery and appearance movement here. So there is absent lung sliding. There are no B lines, absence of B lines, absence of comet tails, and there are more of A lines. Right? So this is again pathognomic of pneumothorax. Then you put a here, M mode here, and you will get a like this barcode sign. So then this confirms that this baby is having pneumothorax. Next, let's come to meconium aspiration syndrome. What happens? There is increased B lines, that is AIS pattern. There is disappearance of A lines. There are pleural line abnormalities. It could be disappeared, thickened, blurred, disrupted pleural lines. There will be subpleural consolidation of various severity. And there will be spade areas in meconium aspiration. There can be pleural effusions and there can be severe atelectasis. I'll show you a video. See, this is a video of meconium aspiration. Here, there is some pleural effusion also. This is a pleural line which is disrupted, interrupted, irregular. Then you can see subpleural consolidations, several degrees, and AIS pattern. And there are absence of A lines. This is how MAS looks. Lung ultrasound can also be used to monitor the response to medical treatment in BPD. In this study, what was done, all the preterm babies were done lung scoring at around 7 days of life. And depending on the lung scoring, they made a prediction that which baby will be having BPD in future. So lung ultrasound scoring also helps us to monitor the degree of severity for the prediction and also its response of the medical treatment to BPD. So in short, this ends the lung ultrasound few points, a few pathological conditions I have covered. And so from my side, the take-home message is that no artifact will give you the exact diagnosis and pathology or disease going on in the lung. It is crucial to incorporate the current complaints, the clinical condition, the medical history, the physical examination, imaging results, and then correlate all of them, interpret the ultrasound findings with that, and then come to a diagnosis. One should first ask yourself, does the severity of the patient's clinical condition correlate with the ultrasounding findings? Just don't depend on your ultrasound findings. Try to correlate it with the FiO2 requirement, clinical condition, your ventilator settings, your CPAP settings, your PEEP requirement, oxygen requirement, FiO2, and only then should a bedside decision be made on lung ultrasound. Thank you, and that's it in lung ultrasound for today.
Thank you, Surjit ma'am, for giving this great talk on lung ultrasound in such a short notice period, ma'am. Thank you, ma'am. Thank you all faculties and participants for being the part of this focus workshop. And all faculties, thank you for sharing your vast knowledge and expertise. There will be the remaining class on the 24th September from 7 p.m. onwards. Till now, good night and thank you all.
Okay.
Thank
Thank you,
Dr.
Vilas.
Thank you, ma'am.
Thank you, Dr.
Thank you, ma'am.
Sujit.
Thank you, sir.
Thank
And
you, sir.
everybody, please remember to log in on 24th. We'll put in the group. Thank you. Bye.
Okay, good night, everyone.
Hello.